A very good morning to everybody, and welcome to IMSc, to all our dignitaries here, and a very happy new year and a prosperous new year to everybody. So it's my pleasure to welcome all our dignitaries on stage. I would request Dr. R. Chidambaram, our dignitary, to just come onto the dais, sir, please. Please, sir. Please, sir. Yes, sir, director, please. Yes, sir. We will. Our director will just escort Dr. Chidambaram. Dr. T. Ramaswamy, sir, can you please join us? Professor Vijay Raghavan, sir, kindly join us. Professor R. Ramachandran, sir, we have a pleasure to inviting you, sir. Professor R. Balasubramaniam, sir, it's a pleasure to welcome you too, sir. Please come, sir. Professor Arvind, sir. Professor Rohini Godbole, ma'am, please. Professor P.D. Nayak, please join us on stage, sir. As we begin this program, I would request all of us to just stand up for the national anthem, please.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
I would now request our director, Professor V. Ravindran, to address the gathering.
Good morning, everyone here. Before I begin, I would like to wish you all a very happy New Year. This is the second day of this year, and we are really happy to have a family get-together at IMSc with our distinguished dignitaries and my colleagues, former friends, students, postdoctoral fellows, and our staff. It's indeed an honor to welcome you for this important function, because it is, here that we celebrated and celebrating, 60 years of IMSc, ever since Professor Alladi Ramakrishnan founded this institute at a very elementary level, in the sense of having a seminar series, theoretical seminar series at his home, Ekampura Nivas, and slowly it grew up to the level that we have quite large number of eminent faculty members who contributed to science in a very big way, and we have been still continuing to do that, actually. So I welcome you all again, and I welcome our chief guest sitting in the dais, who kindly agreed to celebrate this program with us for the next 4 days. I would introduce our chief guest and also welcome our chief guest, Professor Chidambaram. He is an eminent physicist. He is, of course, known to all of us for his prolific role as a principal secretary, scientific advisor for Government of India, and he was a director of BAG and also chairman of Atomic Energy Commission of Government of India, and he was also chairman of the Board of Governors of the International Atomic Energy Agency during 94 to 95. Not to mention that he is a fellow of all the science academies in India and also TWAS, Trieste, Italy. He is also a recipient of Padma Shri, Padma Vibhushan, and I take pleasure to welcome Professor Chidambaram. Welcome, sir, to our program. And I take opportunity to welcome Professor T. Ramasamy. Professor T. Ramasamy is a distinguished scientist who is a former Indian Science and Technology Secretary, former director of the Central Weather Research Institute, Chennai, CLRI, which is close to our institute. He is a recipient of several awards, such as Padma Shri, Padma Bhushan, and among others. And I take immense pleasure to welcome you, sir. And I also take pleasure to welcome Professor K. Vijayaraghavan. Professor K. Vijayaraghavan, a very close friend of IMSc, who is with us. He was a former director of National Center for Biological Sciences, TIFR, and he served as a principal scientific advisor to Prime Minister, who's succeeding Professor R. Chidambaram. He is also former FRS, Foreign Associate of US National Academy of Sciences, and he is also a Padma Shri awardee, and I welcome you, sir. Professor Rohini Godbole, of course, we all know her actually, so please welcome her. Professor Rohini Godbole is a renowned Indian physicist, also my teacher, who is an expert in particle physics, leading advisor to the International Linear Collider in the Europe Research Lab, CERN. She is an elected fellow of all the academies of India and also TWAS. She is a recipient of Padma Shri, National Order for Merit by France and others. And we are all proud of her for all her achievements. And welcome, Professor Godbole. And Professor R. Ramachandran. Professor R. Ramachandran is an eminent scientist. We don't need to introduce to our institute because he was our former director, fondly called RR, close friend of all of us even now, because he visits us regularly. You can see him in the talks that we have even now. He's one of the, the oldest participant in all our Journal Club talks. He served as a former director of IMSc. Welcome, sir. And Professor R. Balasubramaniam, fondly called Balu, was our former director of IMSc. He is an eminent mathematician known for his seminal contribution to number theory. Professor Balasubramaniam is also a Padma Shri awardee. Welcome, sir. and Professor Arvind, our former director, an eminent figure in theoretical computer science. And I would like to welcome him to this program, and he was our director till last year. And it is an immense pleasure to welcome him. Welcome, sir. Professor P.D. Naik. Professor P.D. Naik is acting VC of Homi Bhabha National Institute, India. He has been Dean of HPNI and has been a close friend of IMSc since our association with IMSc. Welcome, sir. So I won't take too much time because we have a lot of things lined up. And again, Happy New Year to all of you, and welcome to our institute to celebrate with us this important event, IMSc 60, and be with all of us actually for the entire program. Thank you. Okay, so there's part of this, this welcome address. I would request Professor Chidambaram to say a few words because he has been with us as a very close friend, helping us to shape this institute. So it will be an honor to have him for a few minutes to say a few words about what he feels.
It's a pleasure to be with you all for this IMSc 60. Of course, mathematics is very important, and in India, the Institute of Mathematical Sciences has been, should I say, the leader or a leader? In the whole of India. And we have very distinguished mathematicians here, some of whom have led this institute, and other distinguished scientists. I don't want to say too much, because anyway I'm going to give a talk, I think. Unless you are cancelled, did you not cancel? In which case I will be doing that. And thank you, I'm delighted that this is being held here. Mathematics is so important I also have how nature uses mathematics. You don't realize it. But all around us, there is mathematics. Thank you very much. I'm delighted to be here with you.
We thank Chidambaram sir and Professor Ravindran for his welcome address. We would now request everybody to be with us because we are going to film a 20-minute film about IMSc. I would request all the dignitaries to kindly take their seats below here, and we will all be viewing the film. Thank you so much. V. Ravindran, who is chairing the first of the scientific sessions here today after the inaugural session, to kindly take over. Thank you, everyone.
Yeah. ಇಲ್ಲ. ಬರಲ್ಲ ಕೇಳ. ಇಲ್ಲ ಎಂತ ಇಲ್ಲ அடுத்தது IMSc இதுதான் சார் சொன்னாங்க பேண்டமிக் 560 தான் வந்துச்சு. வெல்கம் இது பேண்டமிக் இருக்கா எனக்கு எவ்வளோ சார் அவருக்கு ஒரு நிமிஷம் பண்ணிக்கலாம் அதில் இருக்கா கனெக்ட் பண்ணிக்கலாம் சார் கனெக்ட் இருக்கு.
இது டவுன்லோட் பண்ணிட்டேன்.
இது லிங்க்குக்கு போகுது காயத்ரி. ட்ரைவில் ஓப்பன் ஆகும் பார்த்து பார்த்து இது மேக் இது
நீங்கள் ஷேர் கொடுக்குறது
பிக்கப் பண்ணுங்க. பேக்கில் போயிடுவோம். இருங்க இருக்கு. இந்த பக்கம் போட்டுக்கு இது ப்ராப்ளம். கொடுங்க அப்படி இதில் நெக்ஸ்ட் பாயிண்டர் மட்டும் யூஸ் பண்ணி இது இதில் பாயிண்ட் கிடையாது. இது கிடையாது. நெக்ஸ்ட்டு அதுலையே ஸ்லோவாக. ஓகே. Okay, so I'm back with some more things about IMSc. I think it is an opportunity to actually to take a stock of what we have done in last 60 years. Let me just say a few words about how it started. It started by Professor Alladi Ramakrishnan in 1962. It's an autonomous institute under Department of Atomic Energy, Government of India. We are funded by DAE as well as Tamil Nadu government. Okay, so let me just, which is the next one? Moving, okay. Okay, so we have a mandate, of course, like any organization. There are quite a lot of things actually we have been exercising. Our mandate is to create and provide an atmosphere and environment for creative work, pursuit of knowledge, advanced learning of mathematical sciences. We also promote and conduct research and original investigation in fundamental sciences in general, with particular emphasis on mathematics, theoretical computer science, theoretical physics, computational biology. We also foster rigorous mathematical discipline to stimulate a zest for creative work and to cultivate spirit of intellectual collaboration among academic workers, actually, as we saw in the movie. To arrange lectures, meetings, seminars, symposia in pursuance of academic work, and also for diffusion of scientific knowledge among the public. To invite scientists in India abroad, actively engage in creative work to deliver lectures and participate in academic activities. To take such other steps as may be necessary and conducive to the advancement of learning mathematical sciences and also dissemination of knowledge in these sciences. So these were our mandate, and in order to achieve this mandate, we have 4 different groups, as we saw in the movie: theoretical physics, mathematics, theoretical computer science, computational biology. We have different tasks, of course. Physicists, of course, we study wide range of stuff that we see in nature, ranging from low energy to high energy, and string theory to complex systems. Mathematicians here study algebra, geometry analysis, number theory, topology, etc. And our theoretical computer scientists work on understanding mathematical foundations of computations, which include quite a lot of things. And computational biology is the youngest group in our institute. And it's unique in our institute in the sense they actually bring linkage between all the other groups, actually. So this is our strength. Just for those who are not familiar with our institute, we have 48 faculty members at the present, and we'll have more soon. And we have chain of activities throughout the year, starting from doctoral program, which is, I think, our flagship activity here. We are a good number of bright and young students and train them for the PhD program, a rigorous coursework for about 1.5 years to 2 years, depending on which stage they join in our institute. And then they join one of the faculty members in the institute and graduate and leave the institute with PhD. And we also have a postdoctoral program. We get about 40 postdoctoral fellows every year, and they spend about 2 to 3 years in the institute, work independently, also collaborate with us. And we also have summer research program, which is an active program, through which we get the students from various colleges, and they come here and spend time with us, do some reading project, etc. And it provides an opportunity for them to mix with our faculty and students. And we also have associate program, having people from universities and institutions nearby in and around Chennai, and also have a very intense visiting scientist program. We get all throughout the year scientists from India as well as abroad. They come here and spend time with us, collaborate with us. And also we have faculty positions. That's a continuous process that has been going on. because every time we have retirements, we have incoming faculty members actually. So this is how the programs look like. I don't have to say. Just to take a stock of what we have achieved. Currently, we have 126 students, and you will see them soon around this institute and also in the talks in the next 4 days. And we have a constant influx of these numbers, number of students coming for the program. And we also have summer student program that I explained. One of the things that I would like to mention here is that we have an intense outreach activities actually all throughout the year. All the groups actually make an effort to reach out to school children in and around Chennai, inviting them to our institute, teaching them the importance of basic science and mathematics, and that is an important program of our institute. I proudly consider this as actually one of the most important activities in our institute, other than doing basic science and mathematics. We have a very beautiful library, as you can actually visit. We have quite a lot of journals and books and all kinds of facilities, facilitating not only to the IMSc staff people, also to people in the entire southern part of India. Actually, we get queries from all over academic institutions, all over India from academic institutions. We also have a computational facility. We are also going to get a better one soon, actually. And this is a set of pictures, which shows, what kind of things that we have. If you get time, just go around and have a look at, what we have and the facilities that we have for our students. And of course, needless to say that backbone of our institute is administration. A registrar is the head. Under the registrar, we have several divisions helping us. They make sure that we can concentrate our academic activities without any problem. And of course, we had several visitors. These are the earliest visitors I would like to show. As you can see, all these names are actually names that you see in textbooks. So we had an opportunity to have these great people with us at some point of IMSc 60 years actually. But I have left out a large number of visitors here because it's impossible to actually fill. I just quoted. And our faculty members, of course, are well-renowned people. And of course, because of that, actually, I don't have to say that they also are recipient of several awards. And I've not mentioned who got which awards. It's a family, so we are all proud that our faculty got several awards, and I've listed only few of them. And you can see these years that in the brackets, which really tell you that it's not that we have got only once these awards. We are getting every year almost 1 or 2 awards, which are very, very important to encourage our people. And we have several conferences going on throughout the year. There are no year that we can claim that we don't have a conference or meeting. Even during COVID, we had a few meetings, online meetings, and we could actually continue our work as usual. And of course, this is the most important slide. It basically tells you, what we have achieved in last 60 years. And it gives you a nice feeling that actually we are doing great, because the plot basically tells you that we are not, at any point of time or, in a span of few years, we actually, went down or anything. You can see it is climbing up actually. Even COVID time, we had a good number of publications. As you can see, that number of PhD theses that came out from this institute is 309 as on today, and out of which 90 we submitted to University of Madras, and rest of them at HBNI, our university, under which we are also part of it. Actually, publications-wise, we have about 4,275, which basically means papers of the order of 3,000, and rest of them are conference, reviews, book chapter, letters, and etc., etc. So this is the kind of achievements that we have, and I'm proudly congratulate all our faculty members, students, postdocs, and supporting staff for making this to happen. And I confidently say that we will continue to do very well, and you will see after 10 years, our future director will show something crossing this 250 or 300 in this, making all of us proud, actually. So with that, actually, I end by welcoming you on behalf of our faculty, students, PDFs, and staff for our celebration, and welcome to our home. Thank you. And with this, I would like to begin this academic program. The first talk will be by Professor Chidambaram, and I invite him to the stage to deliver the talk. Thank you.
Pleasure to be here. We just now heard from Dr. Ravindran the achievements of the Institute of Mathematical Sciences. And as I said before, IMSc is a leader in mathematics, not just in India, but in the world. We have had some excellent mathematicians who have been faculty members here. And of course, it's obvious that all sciences require mathematics. And that's why I thought I'll talk to you today about the importance of mathematics to other sciences. Talking more generally, the India of our dreams, particularly the young fellows, young people in the audience, is an India which is economically developed, where the Human Development Index is high, which is scientifically advanced, and with a knowledge economy. A knowledge economy is an economy with the ability to generate new knowledge and with the ability to appropriate knowledge generated anywhere in the world with the idea of deriving value from it. And the India for Dreams, particularly the scientists, is a research development innovation ecosystem with excellence in basic research, including what I would call directed basic research, not directed by anybody, but directed by India's needs. Not applied research, but basic research whose value will be derived using technology foresight, selecting the fields in the longer run. Applied research, of course, technology development, R&D-led innovation backed by high-quality manufacturing skills. We also want an India which is militarily strong. Uniquely, we are an economically developing country where parts of the S&T system are highly developed. Of course, this institute itself is an example. We are developed in some areas of defense, knowledge chemicals, and so on. We also need an appetite for risk-taking. Phil Rosenweich in his excellent, in the book, it's an excellent book in which Phil Rosenweich has written an article. He says when it comes to technological breakthroughs or launching new products, it is better to act and fail than fail to act. This is also true of research. When you are taking up different areas in research, it is better to start and fail than not start that program at all. And we all know that you never fully fail. From there some other new ideas and come. Of course, the contrary is to do what is called safe research. You know it will work. You can also get it published in good journals. But is it important? As Peter Medawar has asked, always work on important problems. Important to science or important to society. Nobel laureate Abhijit Banerjee, of course he is an economist, he says, he's talking of economics, poor people take up low risk, low return projects because they fear the risk. So they remain poor. So you can paraphrase it for research. People who want to play safe, take up safe projects, and then the rest of it you can make up. And of course we want leaders. As you all know, India celebrates 4 days in science and technology. Science Day, the day the discovery of the effect named after him was announced by C.V. Raman. Of course, he was the greatest experimental physicist India has produced. Mathematics Day, birthday of Srinivas Ramanujam. Engineers Day, birthday of Mokshagundam Vishweshwaraya, greatest civil engineer India has produced. Then of course Technology Day, the first day of the Pokhran test. C.V. Raman, when he got the Nobel Prize, this is in Vigyan Prasar Science Portal. See, when he told, when the Nobel was awarded to announced, I saw it as a personal triumph, an achievement for me and my collaborators. But when I sat in that crowded hall and I saw the sea of Western faces surrounding me and I the only Indian in my turban and closed coat, it dawned on me that I was really representing my people and my country. I felt truly humble when I received the prize from King Gustav. Then I turned around and saw the British Union Jack under which I had been sitting, and it was then that I realized that my poor country, India, did not even have a flag of her own. And it was this that triggered off my complete breakdown. See, when I was a student in the Indian Institute of Science, Raman Institute was near me, and I have seen him. And he was a very tough, strong man. Very difficult to imagine C.V. Raman breaking down. But it happened here. Of course, today, 75 years after independence, the young people have huge opportunities and they should make full use of it. This is of course Srinivas Ramanujam, and all the mathematicians know. And Srinivas Rao, is he in the audience by any chance? You are, sorry, I almost recognized you. Well, but I was not sure, but he's written a beautiful book on Srinivas Ramanujam, life and work of a natural mathematical genius. Right. Show it to the audience. Yes. See, this is a quote from this book. The natural mathematical genius born in an orthodox Iyengar family is an enigma, the Big Bang, and is a Swayambhu. Many good things in the book, nice books, but this I selected what I like the best. In a short lifespan of 32 years, 4 months, 4 days, he has left behind the famous notebooks containing about 4,000 theorems, which set the mind of Cambridge mathematician Professor G.H. Hardy wonder with awe and admiration, for there were no mistakes at all. The fact that Ramanujam knew but did not write down the proofs of his theorems in his notebooks continues to be a boon to generations of great mathematicians like George Andrews, in fact, who was a discoverer of the lost notebook of Ramanujam in 1976. With the centenary 1987, 125th birth anniversary, celebrated here, no? That is celebrated in math science. And of course it has applications which Ramanujam would have never have imagined in cryptography and coding theory as well. Nobel laureate Chandrasekhar said, as long as people do mathematics, the work of Ramanujam will continue to be appreciated. Of course, just now we heard a detailed description from Dr. Ravindran, but if I classify it very broadly, theoretical physics, mathematics, theoretical computer science, and computational biology gives you an idea of the range of application of mathematics in various areas. Roger Bacon, Bacon is a favorite quotation for me. Mathematics is the door and the key to the sciences. And you look when Bacon lived. COVID was briefly mentioned by Dr. Amindran, and of course it has been modeled, mathematically modeled, to study the disease dynamics, disease spreading. This is an area in which IMSc has interest, and develop prevention strategies against the spreading. The influential parameters are identified and the proper prevention strategies, including lockdowns, are developed. Such modeling has been also done for COVID-19 pandemic. It also attempt to predict it's quite a good work in IIT Kanpur also, and also speculate on whether there would be a next wave, and if so, when. See, the second half of the 20th century has seen the emergence, in parallel with the advent of computers of ever-increasing power, of what is referred to as computational science. And the essence of computational science is the development of algorithms based on mathematical models and their use in simulation. We do that even in condensed matter physics in a very large way. Mathematics is the foundation on which computer science is built, as you all know. But computing is also increasingly used as a key component in mathematical problem solving, of course, computational mathematics. There are theory-driven experiments, and experiment-driven theories also are there. Take the Higgs boson, for instance. The weak force and the electromagnetic force can be described with the same theory. This is the famous standard model of physics. And the only particle they could not see was the Higgs boson. And you know, E is equal to mc squared. Energy disappears, mass disappears, you get energy. That's how the entire nuclear power program is built. But if energy disappears, mass has to be produced. If you read E is equal to mc squared the other way, and they knew the mass of the Higgs boson, 120, 130, 150 times the mass of the hadron, that's the proton. So you needed collisions at least at 4 tera electron volt for a new mass particle like that to be produced. That's what happened in the Large Hadron Collider. And India has, by the way, that was done during my time. See, I have always said India, maybe it's somewhere else in that slide, India is no longer a small in science country. So we should go for international collaboration, but always on an equal partner basis. And the whole thing happened when I was chairing the Board of Governors in IAEA, and one of the Western country guys, and he says, we are suffering from donor fatigue, as though they have been feeding so much to the developing countries. Now they are suffering from fatigue. That's the day I decided that the Department of Atomic Energy will never go for international collaboration on a donor-recipient basis, but only on an equal partner basis. That's how you see in the Large Hadron Collider. It's a 26-kilometer circumference tunnel, 100 meters below the ground. Hadrons, that is, protons are moving in opposite directions. Once in a while, they collide, energy disappears, mass is produced. And they knew, predicting the mass of the Higgs boson, that they must go to at least 4 tera electron volt before you can see this. And hadron, proton, charged particle can be bent by dipole magnet, but it has to be focused by corrector magnets. And in that 26 kilometer circle, 1,800 of the corrector magnet, sextupole, octupole, decapole were supplied by India. At $40 million worth of equipment was supplied by India. So a big place. The same thing with ITER, to which we have contributed very significantly. Of course, theoretically, we have participated. C.P. Vishweshwara, RRI, and Sanjeev Dhoranda, Ayuka, and in this predicting the existence of gravitational waves, and then the LIGO facility. Experimental driven theory is superconductivity. First superconductivity was discovered, then a lot of theories has been developed, Badin-Cooper-Shipper theory, and now Professor Hiroyashi Koizumi has come up with a new theory using the mathematical tool. I will not go into the details. All this involves very high level mathematics to understand what is a very important physical phenomenon. Artificial intelligence and mathematics, you can't have artificial intelligence without mathematics. And the 3 areas which are used there are linear algebra, calculus, and probability. The relevance applications in AI include vectors, matrices, eigenvalues, eigenvectors, and calculus functions, vector, matrix calculation, probability Bayes theorem, to calculate the next step of the robot when the already executed step is given. There you need the Bayes theorem. And other areas that may be needed in AI include information theory, Markov chain, stochastic process used for reinforcement learning. That's not just one-time learning, but you can go on reinforcing the links as compared to supervised machine learning. You can continue to teach it, or it learns by itself. Future, AI and ML are omnipresent. Everywhere people are using We used it, for example, in designing expert systems. 2015, when I was at PSA, we had funded this project in order to be able to predict flooding in cities, flood control. Of course, institution here was involved. Of course, there is a reducing human-machine divide. See, robotics is a part of artificial intelligence. And then many people who are scared, including Professor Stephen Hawking, that one day AI systems may take over the world. I don't agree. I agree more with people like Roger Penrose and some other leading scientists who argue. They use the Gödel's incompleteness theorem to show that any cybernetic system or algorithm developed by man cannot be smarter than the man himself. I agree with that. I think it's pretty obvious to me. Of course, there are super intelligent robots, from artificial intelligence to robots, robots to super intelligent robots. And this is a review of the book on the man who knew infinity, about Ramanujan. And this Isaac Drawer says this is a fascinating book as recognized by the many reviews, but I suggest a different perspective. Namely, the challenge posed by the mind of Srinivasa Ramanujan to the idea of super intelligent robots. Ramanujan was a super genius whose theorems, with novel ideas from his handwritten books, would, at intellectually back-breaking cost, be proved to, yet leave mathematicians baffled that anyone could have divined them in the first place. You see his statue in the entrance to math science. This brings me to the current efforts to spawn robots with artificial general intelligence and beyond, robots with super intelligence. And he concludes, no enhancement of human intelligence opens a door to becoming a Ramanujan, and no algorithm is likely to produce robots with intelligence, with the abilities of Ramanujan. Mathematics in cyber security. See, internet is very convenient. The more you connect, the more convenient it is. But the more you connect, the more insecure you become. So you have to defend the internet. And it's a difficult and continuously evolving exercise. You know the story of two young girls playing even or odd. This girl has kept even. Next time she knows she will keep odd. But if this girl is smarter than that girl, she would know that she is expecting odd after even, I'll keep even after odd. But if this girl is smarter than this girl, she would have worked out. But if this girl is smart, there is a never-ending series here. In a similar way, cyber attacker and the cyber defender, this is a battle which is unending, which will never end, because everyone tries to be smarter than the other. And mathematics plays a key role in both preventing and modeling security breaches, with many cyber security tools and algorithms based actually on mathematical ideas. Take cryptography. Encryption is based on mathematical theory, includes random number generation, which is a very big part of that. And the possible advent of quantum computers in the coming decade, because none is available now, maybe they will come in the next 10 years. It can break any RSA code. Once a quantum computer comes, it's so powerful, it can break any one of these RSA, Rivers-Shamira, Adelman code. And then that's why this field is developing post-quantum cryptography. Once the quantum computer goes, how will you have encrypt information which cannot even be broken by quantum computers? And the sets here, as I told you, which is very close to math science, they are working in this field of post-quantum cryptography. Of course, mathematical statistics, the great man, P.C. Mahalanobis, pioneer in this field of statistical science. In fact, I had gone for his 120th birth anniversary. And India's large-scale economic sample surveys carry credibility today only because of P.C. Mahalanobis. And he established, as you know, the Indian Statistical Institute, but which had started in Presidency College, the statistical lab, and there have been top-class experts in statistical science followed, like Dr. C.R. Rao. Game theory and economics is from a book by Professor Y. Narahari, Institute of Science. He's written a very book. Opposite of game theory is mechanism design. So, and study of strategic interactions among rational decision makers. It is connected to situations where decisions interact, where the payoff for a decision marker depends not only on his or own decision, but also on the decisions of others, which is what happens in normal life. And game theory has been widely recognized, important tool in many fields, particularly economics. John Nash, the American mathematician, is awarded the 1994 Nobel Prize for economics for his landmark work on the mathematics of game theory. So far, Nobel Prize in economics has been won, you may be surprised by this, by 11 game theorists, because game theory has entered economics in such a, this is a quote from Professor Narahari, has written an authoritative book on this subject. Of course, Nobel laureates Abhijit Banerjee and his wife Esther Duflo, who got the Nobel Prize with him, Duflo, and have said that the lack of empirical evidence to back theoretical predictions has affected the credibility of economics. And the Nobel Prize in Economics 2021 has been given to a trio for their work in empirical economics, not just theoretical predictive economics. Biomathematics, use of mathematical models to understand phenomena, many areas of biology, physical biology, immunology, evolution, conservation biology. And the results obtained using model simulation are used to test and extend biological theories, such as new experiments. And then we have computational biology, which included bioinformatics. Of course, there's also biophysics. And the pioneer in this was Professor G.N. Ramchandran, who was next door to both CLRI and Institute of Mathematical Sciences. Famous for his work on collagen. You know, they got the Nobel Prize for solving the double helix structure of DNA. But collagen is a triple helix and Ramachandran solved it. If he had access to that data, which unfortunately didn't have, I think he would have done it much more easily than solving a double helical structure. Of course, he was a very pioneer in this field, and when we were students, we used to go and hear his lectures, and that of Alladi Ramakrishna. We used to come from Presidency College for the lectures that were being suggested by him. And biomathematics use tools like real and complex analysis, integral and differential systems, algebra, geometry, number theory, topology. It's a very, very use is in biomathematics, because biological systems are complex systems. And then, of course, computational biology. Data science has become very popular now in molecular biology, particularly genomics. Let me conclude by something I have been always fascinated by, the mathematics in nature around us, mostly through symmetry. You know, we are symmetric. There are symmetries here in the human body. Many organisms have that. Microscopic organisms, only humans have bilateral symmetry. Distinct and specific reasons why organisms have specific symmetries. Of course, there are so many examples, but I was starfish. It has rotational symmetry. So it can attack a prey from all directions. How nature has created that. Number of petals on a flower follow the Fibonacci sequence. And so many others do. Fractals. You know, fractals is a non-regular geometric shape that has the same degree of non-regularity on all scales. Fractals are fascinating. Makeup for branching of neurons in our brain is decided by fractals. Bees build their hives using a tessellation of hexagons because hexagons cover space very nicely. Concentric circles, a common example is the ripple of a pond. You put it, ripples go. All this is mathematics in nature, which is right in front of our eyes. But we also see concentric circles in the layers of an onion. See, it's all concentric circles. And rings of trees that form as it grows. If you cut it, you can see. Shape of our galaxy is a Fibonacci spiral. Planets orbit the sun on paths that are concentric. We also see concentric circles in the rings of Saturn. We also see unique symmetry in outer space, that is the symmetry between Earth, Moon and Sun. That's what makes a solar eclipse possible. So nature has used all these mathematics in its own way. So I think I'm going to close with another famous quotation by Eugene Paul Wigner. The language of mathematics reveals itself to be unreasonably effective in the natural sciences. So kind of mathematics is omnipresent, whatever kind of scientist you are. So thank you very much. So I enjoyed being with you here.
For this wonderful presentation. And it is also honor for us to actually present to you a small gift. Okay, so we'll move on to the next. Okay, let's move on to the next talk. Professor Balasubramaniam is going to talk about analytical number theory in India.
This will do better. Yes. Thank you very much for this invitation. Yeah, let's talk about analytic number theory in India. This is in some sense a continuation of an earlier article which I wrote. That came in the proceedings of the ICM 2010, and where I discussed the development of number theory in India, especially covering the period from Srinivasa Ramanujan, because a lot has been written about Srinivasa Ramanujan, and but then about the number theorists who came a little later, like Anandarao or Pillai or Vijay Raghavan, nothing much has been written, and I thought it should be, one should probably have those things written. and that essentially covered time till independence. And this is what I plan to continue, and we shall continue this thread and discuss the development of analytic number theory from 1950 to 2000. And for those who are interested in a little later, like 2000 to 2010, there's a beautiful article by Ritapsa Munshi, which appeared in the Indian Journal of Pure and Applied Mathematics, where he covers the period between 2000 and 2010. And he gives two reasons for covering up to 2010. And the first reason is in 2010 is when we had an ICM, and one could have probably see what is the number theory before 2010 and what is after 2010 to see whether conducting an ICM had any effect at all in the development of the number theory here. And there is a second reason to which I will come a little later. Yeah, as I told, I was essentially talking about the number theories of that era, which includes people like Chawla and Pillai. And in that article I wrote, with the departure of Chawla to the United States in 1948 and the death of Pillai in 1950 in an air crash, we leave the first epoch of the development of analytic number theory in India and enter the second. I mean, this first thing and then we second. And again I wrote, if a single event can be said to mark the beginning of this epoch, this is not only in number theory but in any area of mathematics, it is the emergence of the School of Mathematics at the Tata Institute of Fundamental Research under the guidance of K. Chandrasekharan. I mean, to have an institute exclusively devoted for mathematics and having everybody there has always its great effect rather than single individuals working at various places. And of course, most of you would have heard about Chandrasekharan, more as an institute builder rather than a mathematician. He was a great mathematician, but he was much greater institute builder. And in fact, he was not actually the first HOD of TIFR. The first HOD was D.D. Kosambi, and D.D. Kosambi was interested in mathematics, statistics, philology, history, and genetics. And therefore, as a great scientist, he was very great. But on the other hand, Chandrasekharan was not only a great scientist, but a great institute builder. Therefore, let me say something about what he did. KC, as an institute builder, KC joined TIFR in 1948. He was a great institute builder. He persuaded the leading mathematicians like Ambrose, C.L. Siegel, about which I will take a little later, Eilenberg, Rademacher, Maas, Eichler, Zariski, Schwartz, and others to come to TIFR, teach graduate courses to the students so that the students had an opportunity to learn good mathematics from the great mathematicians, and then the lecture notes were written, and that is essentially the. And he also had a 4-year colloquium on various subjects. And regarding this, let me first quote Seshadri about this is what appears in the obituary of which is Seshadri wrote. I still remember that when I met John Coates for the first time at a metro station in Paris, the first question he asked me was, how did you manage it? Meaning, how we were able to build a first-rate mathematics center in India when at that time there was no comparative institution for mathematics in Australia. Therefore, I mean, that achievement of building a great mathematical institute was essentially due to KC. And in Emerson says, MS Narasimhan, in the span of 15 years, KC set up an institute in India which was soon recognized internationally as a leading center of research. And Schwartz writes, this is important, I consider the School of Mathematics of TIFR is a remarkable achievement and is without a parallel in any other country. And that's what exactly Casey did. But on the other hand, Casey was also a great, because now I am going to talk more about the Casey as a number theorist. And in my earlier article, again I wrote, Chandrasekharan's work with Raghavan Narasimhan were the first major work done in the theory of zeta function in India after Chawla. And therefore, probably I should say something about Raghavan Narasimhan also. Raghavan Narasimhan did some number theory in his middle period, which is again what we are going to concentrate, but started more as a person working in functions of several complex variables in the beginning, and he ended also as a function working with the function of several complex variables. That was his forte. And he solved a famous problem in a complex variable called Levy problem when he was 23, on the basis of which he was invited to the ICM. And anyway, we are not going to talk about his work on the complex analysis, which is a major work, but let me just talk about what they did. Yeah, this is Chandrasekharan and Raghavan Narasimhan. Okay, therefore, anyway, when I say analytic number theory, etc., it means a study of the Riemann zeta function and then arithmetic function using the Riemann zeta function. And therefore, I think it's better to fix up some notations of what we are talking about. For a sequence of complex numbers a n and a complex number s, one considers the generating Dirichlet series summation a n n power minus s. And for those of you who might not have seen this, and the fact is, generally we are accustomed to writing a complex number generally as z and its real part as x and imaginary part as y. But on the other hand, this theory was developed at that time when the notations for complex numbers were not well settled. At that time, Riemann used the notation S for a complex number and sigma for its real part and T for its imaginary part. And therefore, as far as the number theorists are concerned, when you say a complex number, it will be always S is equal to sigma plus IT, unlike Z equal to X plus IY for others. This series is convergent in half plane, and in most of the applications we are going to discuss, we will admit a meromorphic continuation throughout the complex plane, and that's very important that it has a meromorphic continuation. And in fact, this zeta function, okay, in particular, if a n equal to 1, then the resulting series is called the Riemann zeta function. And as I told you, this meromorphic continuation is very important because this particular function was originally conceived by Euler. And still it is called the Riemann zeta function essentially because Euler did it only for real variables and Riemann was the one who did it for the complex variable and for analytic continuation. Riemann proved that this function has an analytic continuation with a simple pole at s equal to 1 and also satisfies a functional equation. These are the things which we will be needing when we talk. More precisely, I should write what the functional equation is. It is psi s equal to s into s minus 1 by 2 pi power minus s by 2 gamma s by 2 zeta s, then psi s equal to psi 1 minus s. Among the contribution of Hardy, one should mention the first approximation theorem because this is again something that we will talk about. That is, zeta of sigma plus it is around 1 over n power s n less than or equal to t, where capital T is less than or equal to t. Oh, you should have written. This works when sigma is positive. Yeah, this works when sigma is positive. That's okay. That's what I should have mentioned. Okay, forgot. You see, the point is, you are taking the zeta function and it is not given by the series summation 1 over n power s at that place, because you are now looking at a place S where the function is not convergent. Okay, convergent only when the real part is bigger than 1, but you are taking a place where the real part is less than 1 but positive. Therefore, to say that a function which is not even convergent, but the partial sums appropriately chosen actually approximates the function is something which is slightly interesting and turns out to be very important. And the approximate functional equation, which is again the same thing. I mean that you take the zeta function and take the partial sums, you take the chi s into zeta s, zeta 1 minus s, take the partial sums, add it, and it approximates zeta function even at a place where this series are not convergent. Okay, it is easy to see that the functional equation that the zeta function has zeros at negative even integers, therefore at minus 2, minus 4, etc. And the celebrated Riemann hypothesis states that all the non-trivial zeros have their real particle to have. Anyway, okay, what is our interesting question? The question is, we would be interested in deducing the asymptotic formula for the symmetry function of an from the analytic properties. Therefore, you study sigma an into n power minus s and then try to deduce something on the asymptotic formula. More precisely, we would like to prove that summation an is some capital M of n and plus E of n, where capital M is the expected main term, the dominant term, and En is an error term or the secondary term. Results of the type En is small as a function of n, to say that Mn is around n and En is around less than square root of n. Those results are called O results, and En cannot be very small. There are n's for which En is at least as big as n power 1/4 or something like that, will be called omega results. Okay, now we go to the work of Chandrasekhar and Narasimhan. Chandrasekhar and Narasimhan considered the Rees mean of the sequence, which is, and then used it to get the O result and omega result for the symmetry function. And I need not say how important the result is, just to say that it got published in Annals 1962. And they applied this to study special arithmetic function like a divisor function, Euler phi function, etc. In 1964, for the same thing, they obtained the L2 estimates for the error term. In 1963, they proved, this had turned out to be one of the very important papers quoted again and again, that for any Dirichlet series that has a functional equation, under some mild condition, one can write an approximate functional equation. Remember, this was done by Hardy for the zeta function. But then they said that you don't need to just restrict yourself to zeta function, take anything which is a functional equation. From such a generated setup, they could get an approximate functional equation for the zeta function of number fields, because the zeta function of number fields, etc., do have a functional equation, and then they were able to do a lot on that. This idea has been extensively used by the later authors. And now we leave it at that, and then Raghav Narasimhan left TIFR around 1964, and Chandrasekharan left it around 1965, and therefore now there was somebody was needed to really have the number theory developed in Tata Institute, and that was aptly filled by Ramchandra. And in the rest of the talk, probably next 10 minutes, I will be just talking about some work of Ramchandra. And in fact, I already mentioned about Munshi's article covering the period 2000 to 2010, and one reason he was closing in 2010 was essentially because of the ICM. And the second reason, he writes, at a more personal level, K. Ramchandra, who spearheaded research in analytic number theory in India, passed away in January 2011, bringing an end an era. Therefore, if at all you want to say that the second epoch, which is around from the independence to 1990, etc., it was essentially dominated by Ramchandra in analytic number theory. Ramchandra joined TIFR as a student in 1958. See, most of us would join a research institute immediately after our MSc, but due to some personal reasons, Ramchandra could not join immediately, and therefore he joined a couple of years after he finished his MSc. And, but already he was well equipped to start a research career. And looking at that, KC decided that Ramchandra need not undergo the standard customary graduate courses. And probably Ramchandra was the only exception who did not have a graduate course. I don't know what would have happened if he had gone to the graduate course. Yeah, he was inspired by, at that time, again as I was telling, KC was getting great visitors to Tata Institute to teach to the young kids. And that year it was C.L. Segal. And Ramchandra was inspired by the course of lectures given by Segal and wrote his thesis on a problem suggested by Segal under the supervision of K.G. Ramanathan. And I am not going to talk much about things. This is Ramchandra and this is K.G. Ramanathan. Okay, I'll just say what this thing is. Mathematical reviews. Eichler starts with the comments on this paper. This paper contains some remarkable new results on the construction of Ray class fields on an imaginary quadratic fields. Okay? And I don't think I will be able to explain any of those terms now, and that would already cross the time limit which Ravindran has set. And in this paper, he also constructed a set of units and the evaluation of certain elliptic integrals. And he got interested in these elliptic integrals essentially because they were constructed by Ramanujan. Then I should probably say something more. What did I have? Good. This is, Ramchandra is not really very good communicator, whether orally or writing. It is a little difficult to understand. And I can count myself as one set of people who could understand him. And I had to, because I have taken I have decided to join him as a student, and I cannot now give an excuse that I cannot understand what you are saying, and therefore, I had to force myself to understand what he has to say, and turned out to be more or less I am the only person who could really do that. And in writing also, he was not very good communicator. This is important because in 1970 ICM, H.M. Stark was giving a lecture, and where again he was essentially talking about the construction of the Ray class field, which at that time was a conjecture, which was a very important conjecture. And then before he finished that thing, before he gave the lecture, Ramchandra came up with his beautiful proof, and therefore he has to add a few lines that this conjecture is now no more a conjecture, it is a proof. And that's exactly what he writes. Unless I have missed something, the proof is a simple matter of deciphering the notation of Ramchandra and applying his results. Okay? That's what it is. And then he did something on transcendental numbers. Since I don't have time, I have to. Okay. The youngsters can see on Ramchandra's contribution to transcendental number theory. And it's around the time Baker proved his important theorem, and Ramchandra, along with his student T.N. Shori, made some important contribution towards the theory and applied it to a whole of differential equations. That itself is a great thing, but I am not going to talk about that because for two reasons. Number one, it's a lecture on analytic number theory, and number two, I was nowhere involved in those work, and therefore I cannot talk about myself if I start talking about that. Okay, around 1970s, his interest towards theory of Riemann zeta function, it is at that time I joined him as a student, and we shall briefly discuss some of the results which came out of the Ramchandra school. Let Fs equal to sigma an by n power s be a Dirichlet series which is absolutely convergent and admits an analytic continuation. Let T and H be two parameters. Here H is a small power of T, and Ramchandra found a method of getting a lower bound for the L1 norm and the L2 norm of f of it in this interval. And this turned out to be rather very important. In particular, he proved results of these types. Okay, this is appeared in my thesis. My thesis also contains some results related to the result of Titmarsh on the L2 norm, and a method called multiple averaging to get the O result. And the Hardy was the first one who proved that there are infinite limit zeros on the Riemann zeta function on the critical line. And he proved that if h is equal to t power 1/4, then you can find out a t in the interval t to t plus h such that the zeta function vanishes at O plus it. Though the multiple averaging and the lower bound for the L1 norm due to Ramchandra enables one to conclude the same for h equal to t power 1/6, improving the result of Hardy. Ramchandra showed how to get the lower bound for the fractional powers of zeta function, and about which Heath wrote that he could not even believe that the results would be correct at all. And these results turned out to be very important for trying to see the random matrix theory, how much it can apply to the Riemann zeta function. Therefore, these are the type of results which he proved, and this appeared in that. And Ramchandra used this method to get an omega result for the values of zeta of O plus it. For example, it is known that zeta of O plus it can be bounded by exponential constant times log t by log t. And now it is possible the omega result, which means that it is at least as big as exponential constant times log t. And Soundararajan, I don't know how many of you know him, I mean probably. Okay, Soundararajan observed that this method gives a value of 0.57, which remained the best for a long time until Soundararajan showed how one can take c equal to 3.7 using this resonance method. And I was talking about the lower bound for the things, and if you are thinking of an upper bound for the moments of the zeta function, the best results for the upper bounds are due to Soundararajan. Another important application of the lower bound in short intervals to get omega results. Okay, these are the things. And let me not briefly discuss the content, but just say why it is important. Yeah. Ramchandra's observation, you see, first of all, if you have integral t to 2t f of a plus it whole square dt is bigger than t constant times t square, then you will get an omega result. E of t is O of t power a. And the only thing which you need is a certain sort of a holomorphicity. And Ramchandra's observation was that the result remains valid even if there are a few singularities, which it turned out to be important because in most of the problems there will be singularities, and therefore you cannot apply the standard Perron's formula, and there are standard Parseval's formula, and somehow you have to handle it, and Ramchandra was the first one who showed somehow how to handle that. Yeah, for example, he applied it to the function zeta 2s, zeta 3s by zeta 6x. Okay, this method turned out to be powerful by many to prove omega result. Therefore, let me just quote from Kortner and Novak. The method of proof, which turns out to be appropriate in this problem, goes back to the ideas due to Ramchandra, Balsuddin, Ramachandra, and Subbarao. They have been worked out in papers by Schinzel, Kirchner, and the authors. I mean, many papers came actually explaining the ideas behind that. And this is the one thing which I want to talk and then prove. The method of proving non-vanishing on the line is to connect the value of zeta of 1 plus it and 1 plus 2it. This method also gives a zero-free region. And Ingham observed that without connecting 1 plus it and 1 plus 2it, you can argue only at 1 plus it using the following identity due to Srinivasa Ramanujan. This gave a non-vanishing but not a zero-free region. And Ramchandra observed that one can also get a zero-free region from this identity of Ramanujan. Now, in the very funnily, 1930, Ingham proved it, and I think there has been no development at all on that observation till we came around 1976 to make a thing, and again around for 30 years there has been no improvement at all. But now recently people have started thinking that this idea can really be used. For example, Peter Sornak has used this idea, and Humphreys and Brumley, let me quote it, the method of proof is of particular interest. It is essentially a generalization from GL1 of AQ to GLN of AF of the method of Balsuddin and Ramchandra. How much Ramchandra would understand that and appreciate that is our thing with SPC. Ramchandra developed a method to deal with overresult for the summatory functions, and in order to show the error term solved, we will ordinarily move the line of integration. In a number of interesting cases, this is obstructed with the presence of algebraic singularities, and Ramchandra developed a method called Huxley contour, essentially using the fact that the number of singularities are small to really do the things, and this is one of the very nice paper of Ramchandra in Acta Arithmetica. This still remains the best method for getting summatory function. Okay, I think I would stop there.
Thank you for wonderful presentation. And something for you. We try to bribe everybody before. Small gift from us.
Thank you. Good.
Let's move on to
Sorry,
the last
you
talk
should
of
take
this session. Professor P.D. Nayak, officiating VC, Teen HPNI, is going to talk about Homi Bhabha National Institute.
Good morning, and as many of you might be knowing that IMSc is academically connected to the Homi Bhabha National Institute, and there are some facility in Homi Bhabha National Institute, deemed to be university. This is much different from conventional university. That point only I would like to bring it here. And also I'm going to bring out some of the achievements of the IMSc students in HBN, in its ranking and many other things. In fact, our founder director, R.B. Grover, he had written many articles in Current Science regarding how it will be beneficial to bring together the infrastructures at various education institutes and research centers together for developing new technologies as well as advancement of science. This is not new. If you go JPL, Jet Propulsion Laboratory, it is very much connected with University of California. And most of the academic brainstorming at JPL is due to its association with California University. So apart from this, there are many other things like Sogendai at Gateway University for Advanced Studies, established in Japan in 1988. And it is running only doctoral programs like ours also, I can tell you afterwards. Brings together several research institutes and museums such as the National Museums of Japanese History. Most importantly, recently developed Paris Sacré University, which was formed in 2015 but recognized as a university in 2019. And it is, the university shares 275 laboratories with several research organizations, including CEA, Atomic Energy Alternative, INSERM, French Institute of Health and Medical Research, and others. Although it is formally recognized in 2019, because of strong research in these 275 laboratories, academic ranking of world universities, Shanghai ranking, it was ranked number 14 in 2020, and now in 2022 it is number 16 worldwide. As this shows that how bringing together the research institutes together beneficial to the university as well as for the country. For DAE, always connected with the academic things, and Homi Baba started BRC Tennis School right in the 1957. At that time, it was known as AET Tennis School, and tennis were observed as the officers. In fact, most of the scientists who were joined in Baba Atomic Research Center at that time, afterwards in IGCAR also and other things, they were carrying out the research programs, obtaining PhD degree from different universities. As well as in aided institutes, there are many students with the faculty at aided institutes, and they were registered with the university nearby to the institute where they are located. And with the expanding research needs, it was felt that appropriate that all academic programs in DAE are brought together under one umbrella. In 2003, DAE Science Research Council with Dr. Raja Ramanna in chair recommended that in DAE may establish a deemed university. HBNI was established as a trust and society in 2005. It was given recognition as a deemed to be university by UGC on June 3rd, 2005, and academic program started in 2006. As you know that we are a granting institute of DAE with effect from February 19, 2014. University has distributed structures, and it brings together academic programs of 11 premier institutes of DAE, comprising 4 R&D centers and 7 granting ed institutes. And these are the R&D centers: Baba Atomic Research Center, Indira Gandhi Center for Atomic Research, Kalpakkam, RRCAT, VCC, and IPR, SINP, TMC, IMSc, HRI, IOP, and NICER. At present, HBNI runs 48 academic programs in various disciplines. And major strength is like perisaccharic or other things. Our major program is the doctorate programs. Out of total 3,261 students on roles on date, 1,876 students are PhD students. Office, previously there were very number of employee students. Now we have out of 1876, 1269 are students. They are not employees of any of our institutes. HBNI also offers the facility and super facility programs, MD, DM, MCS in oncology and radiation medicines. HBNI offers several unique programs that are skill-based programs. And most of the graduates which are taking the skill-based programs are immediately getting employment in hospitals and many other industry and other organizations. We have started recently introduced the following programs: PhD in Earth and Planetary Sciences, PhD in Humanities and Social Sciences, PhD in Computer Science at NICER, MSc in Medical and Radiological Physics. And we are also about to start MD, integrated MD PhD programs, MSc in Patient Navigators under the Medical and Health Sciences Board of Studies. This is really unique structures: admissions, coursework, examinations, as well as day-to-day administrations and mentoring of students are under the purview of the CIOCC. Approval process for enrollment, constitution of doctorate committee, examiners for thesis review, declaration of results are under the purview of the center office at HBNI. Design of the academic programs in line with the missions and objectives of the institutes is under the purview of the CIOCC, because each CI and OCC have their own missions and objectives. As IMSc director already shown the missions of IMSc. However, the syllabus of the courses are approved by Board of Studies, which have members from all CIOCC, and these courses and programs need approval of the Academic Council. Again, it is a distributed structures of HBNI. All these academic programs are conducted, as I told you previously, at campus office CIOCC. All faculty of HBNIs are on the rolls of CIOCC. Only VC, Dean, and Registrar are on the rolls of HBNI. Director of CIOCC, Standing Academic Committee at CIOCC, and Deans at CIOCC oversee the implementation of academic programs pertaining to their units. So basically, I will show you afterward the structure. The center office to forums such as Standing Committee of Deans, Board of Studies, and Academic Council ensures adherence to a common system of academic standards and processes, and catalyzes synergic interaction between faculty and students at various campuses. For better interactions, we have recently started an interaction meeting at various CIOCC. Condensed matter physics was conducted at SINP. Then in life science at RRCAT, and two more are in the pipelines and coming soon. Interaction meeting in chemistry will be held in NICER, and again one more interaction meeting in life sciences will be held at SINP. The center office is responsible for interactions with statutory and regulatory bodies, accreditations, NAC, NRF, and implementation of various regulations. This is structures. Top, if you can think about, this is a HBNI center office, and now it is being held by the Standing Committee of Deans, Board of Studies, advised by the Academic Council, as well as the highest body, the Council of Management. All the academic programs at the CIOCC are looked after by the Director of CI, Dean Academic, Doctorate Committee for Individual Students, Guide, and then they will be helped by the Dean Student Affairs. And Dean Student Affairs are also a part of the Standing Committee of Deans. In the other unique features are that faculty of DE R&D centers, they are not faculty as such, they are the scientists and engineers at various R&D centers. And they are pursuing the mission programs as per departmental requirements, at the same time mentoring and guiding the research students, giving courses, participating in doctor and other committees. And these faculty are not getting additional compensation for this academic responsibility. Presently, over 70% of research students are non-employees, and these students constitute a bright and dynamic protein populations, contributing significantly to the research needs of the department. We have the collaboration with the various eminent institutes in India for credit transfer, joint guide and co-guide. And the fees for students to attend these courses is made by HBNI. These are how, after permission of the HBNI, number of MD, DM, MCS has been increased. In 2011, 10-11, you can see only 4, and now it is more than 150. Number of PhDs now, last year 2022, we have around 253, and totally we have awarded more than 2,150 PhD degrees. And as IMS also have the major share, one of the share around 219, as Dr. IMS has mentioned about that. You see, about about the quality of the thesis. It is important, and average journal papers per thesis produced by HBNI is more than 3, and most of them are in the respective field as published in the high impact journals. So average general impact factors per papers published by students is greater than 3. Various board of studies have fixed minimum number of papers, like chemical science is 3, and definitely in life science 1, mathematics science 1, and like that. So average general papers per thesis for chemical science are greater than 4, engineering science greater than 2, and like that. In fact, coming to IMSc from 1st of April 2021 to 31st December 2022, IMSc has produced 37 PhD degrees, and in the year 2021-22 it was 24, 30 more added in this 9 months. And we can see that most of graduate students in IMSc or in other CI, OCC or HBNI are well placed in various, and Meena Mahajan mentioned about that, they are not only contributing to the academic, they are also joining industry and helping the industry R&D. And this person had not mentioned about that, he is also placed. So like that, similarly in physics, mathematics and other things, they are well placed. Coming about the ranking, which HBNM accredited by the National Assessment and Accreditation Council with the grade A+ in 2001. NRN ranking of MHRD for the year 2022, HBNM was placed at 17th rank among universities and 11th rank among research institutes. Nature Index ranking based on the publication in 82 high impact journals, HBNM was placed 2nd position among all Indian institutes, which is covering all disciplines, and first with respect to physical sciences for the period April 21 to March 22. So this is definitely a contribution from all the CIS, OCC of HBNI and IMSc as well. I thank for all the students and faculty at IMSc as well as various CIS and OCC because contributions are mainly from CI, OCC and not by HBNI Center Office. I want to make it clear. In HBNI Center Office, we are conducting various varied courses, Newton's proof of condensed matter, design of multiple reactors and contactors, and many other courses we have conducted, and which are taken by students of HBNI as well as students from various eminent institutes like IISc, IIT Bombay, ICT, and other things. And 2 of our courses recently, apart from various courses by CIOCC, Newton's scattering and accelerator physics are being offered on the NPTEL platform. And first year itself in accelerator physics, we have more than 2,000 registered participants. Recently, we have created the HBNI Industry Linkage Centers, known as SILP, and to facilitate the internships of the student in industry, because apart from academic, the bright students should go to the industry for developing various R&D programs in the industry and developing the new products. Enable R&D collaboration between industry and HBNI students and faculty. This year we have not yet started. Third one, we have already started the interaction of industry with the ex-scientific and technical experts from DA units. We are getting a lot of requests from the industry because we have, at present in our website, we have given the names of the consultant. Most of them are our ex-scientific and technical experts from DRC, IGCAR, many other things. And industry going through this, and we are getting the request from industry to have the consultancy from HBNI involving these experts. With this, I thank you.
Okay, there's a present for you actually. Thank you very much for telling us about HPNA and its achievements. We have a small presentation for you. A short announcement, because we are running out of time and schedule. We would like to have our tea session shortened by 15 minutes. So let's quickly have tea outside and then come back. So we'll say 15 minutes. We're going to say 45 minutes during lunchtime and the next tea session. Thank you.
So welcome back to this second session in the IMSc 60 program, and I'm very pleased to start off the session. The first talk is going to be by Professor Rohini Godbole. You heard our director introduce her earlier this morning. She is a professor at IISc Bangalore, and today she's going to shed some light on dark matter. Afternoon now to all of us, and I thank Ravindran for inviting me here to give this talk. As I mentioned to somebody, if I begin by talking about my association with math science, as well as all the friends I know in math science, the talk would be over. So I'm not going to do that, but I should say that my association with math science, however, I should say when it began. It began during the directorship of Professor E.C.G. Sudarshan when I was a young postdoc at the Tata Institute of Fundamental Research. And I'm glad to be giving this talk here today when one of the students I knew from my early days of visits to math science is today the director of math science. And in between, I have, visited here, collaborating with friends like Saurabh Rindani, then Rahul Basu, then I have also interacted and worked with Indu, with and so on, Sri, and so on and so forth, and Ravindran as well. And apart from physics, there have been a lot of friends. And I say congratulations to all of them on the occasion of the 60th birthday of math science. And I noticed that math science is only 10 years younger than I am. So I decided, when I thought what to talk about, I decided that I would give you a flavor of one of the topics that is right now at the forefront of research in particle physics. And luckily, I have been able to sort of tell you at the last 10 minutes of the talk about a result which we got recently, and it is kind of a conclusion of study which I had been doing with various people over past 20, 25 years. And we have got a negative but a conclusive result, so I thought I'll share that with you. So, this happy birthday math science. What will I do? So, as I said, dark matter right now happens to be at the forefront of theoretical and experimental research in particle physics, as well as what I would call broadly astroparticle physics. So I'll first tell you what is dark matter, and then I would go to something that has been one of my sort of pet baby, and that is what is the supersymmetric dark matter. And the supersymmetric dark matter, I will introduce a word. Following Balu, I will also introduce notations. So the lightest supersymmetric particle, I will call it LSP. And I will explain what that is. And then my talk is really about low mass dark matter in supersymmetry. And by low mass, I should set some scale. So I would be talking strictly about a dark matter candidate with a mass less than half the Higgs mass. The word Higgs has been mentioned already, and also Gautam will talk about it in the talk after lunch. But that is one quantity that we particle physicists know quite well, and it is 125.2. So a dark matter particle which is less than 125.2 divided by 2 is what I am going to be talking about. And I will actually cover only what is written in olive, that is one dark matter, lightest LSP, lightest supersymmetric particle. But the pointer, does the pointer work? Ah, yeah, here it is. Here. But I will only talk about this LSP in a version of minimal supersymmetric standard model, which is the popular beyond standard model physics that particle physicists have been studying for decades and not finding any evidence for. The remaining things in the red are only written for the experts in the audience, that there is related work that we have done, and I will not be talking here in this talk about it. The particular PMSSM part that I mentioned is actually based on these 3 or 4 papers that we have written recently, and about this latest result that I'm so excited about is in this paper, which is still under consideration for publication. So what is dark matter? Apart from saying that this is one subject over which a very large number of particle and astroparticle physicists are working, I should say something more. So what is that? Dark matter is literally matter that does not shine. And in other words, it's a matter, obviously matter has gravitational interaction, so it's matter which has gravitational interactions, but it does not have any interactions with light. This was postulated by Zwicky in about 1933, but really solid evidence was established by very detailed observations by Vera Rubin in 1970. And here I may put on my hat as a female physicist and say that it's a great pity that Vera Rubin never got the Nobel Prize that she deserved for this. But anyhow, that's the way things go. Now, over the past decades, the evidence for its existence, the existence of the dark matter, has actually grown, and it's at all distance scales. Now, what is meant by distance scales? So this is where the astro part of the thing comes in. When I say distance scales, I actually talk about kiloparsec, megaparsec, and gigaparsec. So what is 1 parsec? For some strange reasons which astronomers use, 1 gigaparsec is 3.2 light years. Don't ask me why. So it is the distance that light travels in 3.2 years. And we are talking of kiloparsec, megaparsec, and gigaparsec. Just to give you a sense, the distance from sun to earth is 8 light minutes. And distance from earth to Jupiter is 43 light minutes. So that should give us an idea the distance scales at which the dark matter existence has been demonstrated and proved conclusively from a series of astronomical and cosmological observations. What we also know that the dark matter forms 26.8% of the energy budget of the universe. What we also know that it's something that moves around continuously with a velocity of about 200 kilometers per second. And as I said, the direct experimental evidence exists only of its gravitational interaction. It has to be electromagnetically neutral because we don't see it. And it has got to be stable on the scale of the lifetime of the universe for the simple reason that the only idea how it could have been created that we have right now says that it was created at the beginning, in the first, not exactly in the first 3 minutes, but little bit after the first 3 minutes. And the dark matter has actually provided the attraction to bind matter together to form galaxies, stars, and everything, all the structures that we see. So again, the astrophysical evidence is very strong, and these are relics left over from the early universe. Okay, maybe before I go and say, so what? The point is that none of the, we particle physicists pride ourselves in saying that we now know the list of all the fundamental particles. And the funny part is none of those fundamental particles in the universe can be this dark matter. Which means that this is unknown to us. It's a completely unknown entity. And this is in spite of the fact that we have this wonderful standard model which was mentioned by Professor Chidambaram. So this is indeed a mystery. Now, calculations of the expected relic density is actually can be done, and it is actually affected by 2 things. One, that is our understanding of the early universe, which involves standard model of cosmology, and the particle content of the particles in the early universe, which is mostly controlled by the standard model of particle physics. And there must be something beyond standard model at that time of the universe. Otherwise, we wouldn't have had this dark matter hanging around here. So it's a real mystery what it is. And actually, I mentioned that it has implications for structure formation in the universe. So it is somehow saying that in the early universe, dark matter provided the potential wells in which matter formed, matter fell, and that's how all the structures got formed. So that is something therefore, from very complicated ways, by observations of cosmic microwave background radiation, people are able to establish how much is the amount of this dark matter. And in all these theoretical calculations and the observation, which I will show in the next slide, one actually likes a particle which would actually be moving at non-relativistic speeds. All of us know that at speeds much less than the velocity of light. At the time, it decoupled from radiation, because in the universe was originally only radiation, and somewhere along the line, matter was formed. So this, we like actually a particle which is actually non-relativistic at the time it decoupled, and therefore that is called a cold dark matter, very picturesque. And this cold dark matter was something that particle physicists liked very much, because the standard, beyond standard model physics, which I will tell you in next slide, which is supersymmetry, had a ready-made candidate for this. And that's why we were all very thrilled when decades ago, astrophysicists, cosmologists told us that their dark matter should be cold dark matter. So we were very, very thrilled, and that is where we were beginning to started working on it. But now this whole paradigm has come under tension, and the reasons for tensions I will give you in the next slide. What has happened is that famously we have found the light Higgs boson at the Large Hadron Collider 10 years ago. What is meant by light is that it has a mass of 125 GeV, which is close to the mass of the W boson and the Z boson, and not 10 times or 100 times after that. So that's what it's meant by a light Higgs boson. And theoretically, again the power of mathematics, theoretically physicists have liked supersymmetry as a possible postulated existence of supersymmetry, because it would actually explain why the observed Higgs boson is light. And as I said, the bonus was that supersymmetry had a ready-made dark matter candidate. So first, there exists a dark matter. We have very good measurements. I'm going to tell that in half a slide ago afterwards. But supersymmetry theories, which is what many of us spent a lot of time over the last decades, it had a ready-made dark matter candidate. And as I said, there are many other reasons why SUSY was the most attractive beyond standard model physics. And in other talks given in this auditorium, I have expounded on that. But today, I'm not going to tell you much more about it. So most of us grew up in the period when SUSY was the standard beyond standard model physics, because this is one of those beauties where the internal consistency of the standard model had told us that there should exist some physics beyond standard model. The existence of dark matter gives me experimental evidence that there is some physics beyond standard model. Our liked model of beyond standard model physics has a natural candidate for this dark matter. So you see how exciting it was that one thought that yes, once I found the light Higgs boson, now the Large Hadron Collider or some other experiment are going to find me the proof of the existence of this dark matter. And that is something even before the Higgs was discovered at the Large Hadron Collider, as I will show you. Many of us were working on how one can look for such a dark matter candidate in different dark matter experiments. And in case I don't get to the end of my talk, what I'm going to show you, what we found very recently, that in this limited mass range that I'm talking about, we have been able to conclusively prove that all the sets of experiments now tell us that a dark matter candidate which is supersymmetric cannot exist below the mass of half the mass of the Higgs boson. So at least this is giving you why I'm excited about it and why I want to try and share it with you. So firstly, the Large Hadron Collider found the Higgs, but it did not find any other evidence for supersymmetric particles. And all the efforts in the last 10 years have failed. They have only put bounds, bounds, and bounds. And in addition to that, there have been actually underground experiments, and I will use these names in a few slides again. And they have put actually this paradigm of weakly interacting massive particle as dark matter under severe stress. So you have two sets of experiments, very beautiful experiments, but negative results have put this whole idea which is theoretically and mathematically extremely attractive under a lot of pressure. And therefore, as a good theorist who loves a theory, we wanted to see, can we look for some region which has been left out because of these searches, and can we find the evidence in some nook or cranny? And as I said, the result is negative. We find that it is not lives in that some nook and cranny, under very minimal assumptions. If I change the assumptions, things may change. So what is the point? The point is that Large Hadron Collider has only produced constraints on the masses of a number of supersymmetric particles, and usually these constraints in a theoretical framework translate into parameters of the theory. I don't need to tell you what the parameters are, and they are large in number. So about 100, if I were completely free, there will be 123 parameters, but certain theoretical ideas reduce those number of free parameters. But all said and done, the experimental non-observation at the Large Hadron Collider of a whole lot of supersymmetric partners of standard model particles has put constraints on the SUSY parameters. And they are constrained to have very high values. But in all this, the only particle that is allowed to be light is what is the lightest neutralino. Let me define what this neutralino is in the next slide. In supersymmetric theories, there are two natural candidates for that. First, to begin with, there is no candidate for dark matter in standard model. Neutrino could have been that, but experimental observations told us that neutrino is not the dark matter. So let's leave that. In the supersymmetric theories, there are two candidates. One is the supersymmetric partner of the neutrino, which is called sneutrino, and the neutralino. A neutralino is actually a combination of supersymmetric particle of the Higgs, which are called Higgsinos, and the supersymmetric partners of the W and Z bosons, which I will generally call electroweakinos. So again, definitions, names. So the neutrino actually has full strength gauge couplings to the standard model matter. As a result of that, the detection experiments which tried to detect dark matter have proved that neutrino can never be a dark matter candidate. So we rule it out, and the simplest pictures. And the weakest LHC constraints are from non-observations from the LHC are on the mass of the neutralino. So that is a linear combination of the Higgsinos and electroweakinos, and I'm going to focus on that. So when I say low mass constraints, you will realize that the current constraints, this is from the latest 2021, it says that the LSP, roughly speaking, in some generic models, has to be, the constraints are beginning to rule out LSP masses in this small region, and then this is the region that we wanted to critically evaluate, because these limits here actually depend on certain assumptions. So we decided to critically evaluate the case of a light LSP and in general a light electroweak sector. And as I said already, we have been able to show that certain values of a light neutralino mass are almost ruled out if we demand consistency with a number of different experiments, both at the accelerator, in the ground, and in the sky. So that is basically the major lesson. Now theoretically, do we expect electroweakinos to be light? So the master, which I think all of, even non-physicists would know about him, is Steven Weinberg. And as a matter of fact, this paper was the reason why I started doing supersymmetry, because he had written a paper in 1983 showing that electroweakinos can be the lightest parts of the supersymmetric particle spectrum under some theoretical conditions. So this means that if at all there is a light supersymmetric particle, theoretically, which is light, it would be the lightest one in the, no matter what the spectrum is likely to be an electroweakino. Then there are these measurements by Planck. Planck was a satellite-based experiment which actually measured the anisotropies in the cosmic microwave background radiation, and it gave us this rather accurate measurement of the total dark matter density. H here is the scaled Hubble constant. So again, this is the astroparticle language. So this actually told us that the total dark matter density in the universe is 0.120 plus minus 0.001. So it's a pretty accurate measurement, and growing in an era when cosmologists, we used to ridicule cosmologists by saying that their errors are in the exponents in the measured quantities. Now here there are 1%, 1 per mil measurement of actual energy density in the universe. Now in a model, like a theorist, like most of us, we can compute the predicted density. Again, I won't go through all the details, but we can predict that the same quantity that is being measured, we can predict in our models, and what is the controlling factor there is this cross-section where the two dark matter candidates will annihilate into whatever it will do. And this sigma cross-section of this annihilation times the velocity with which the dark matter would be moving at that time, this is the quantity which really controls in a model the prediction of what a model will predict as a relic. I mean, obviously, if I start with a model and it predicts a relic which is 10 times what has been observed, the model will be thrown out of the window the minute I write it. So therefore, that calculation is a very important part of the exercise. And as I already said, if the computed omega h square is much bigger than the measured one, the theory would be inconsistent with the observed flat nature of the universe. So that's a very important piece of information. You cannot muck around with what the universe is like, so you have to throw away that model. All right. Now, how do you detect it? You detect it in 3 different types of experiments, and I will use these words, so I will please again definitions. DD means direct detection, indirect detection as it is, no definition, and collider searches which are at the Large Hadron Collider. I have what I will say here has bearing only on these 2 sets of experiments, but by and large these experiments also play an important role. So, what is the current experimental status of detection of dark matter? First, I told you existence of dark matter. That's very high. That's very accurate, 0.120 plus minus 0.001. There is not much space left. Whereas, what is the detection? There has been a whole lot of, again, this is a very changing scenario. But what I want to show you here is how quickly the direct detection limits scenario has been changing. In 2018, what the experiments did is that they looked for dark matter. I showed you this. In this experiment, these are these major big detectors of xenon, which are again underground and very complicated experiments. I wouldn't even be able to tell you all the details. And they did not find evidence of a dark matter, of the warm, what is called WIMP, I told you, the CDM. And they only put limits. And they said that all we know is that if a dark matter candidate exists with a mass 10 GeV, its cross-section should be less than 1 point into 10 to the minus 16 centimeters square. That's all it can tell you. Now, this limit actually readily improved quite quickly for larger masses in 2021. And right now, this is very recent, 2022, this is called the LZ result, and these are the 3 experiments I was telling you about, Xenon 110, Panda X, and LZ. And LZ has been actually the one which has now put a limit on the cross, said that at 30 GeV, a good mass for CDM and a good range, here the cross-section, all the values of the cross-section above 5.9 into 10 to the minus 48 centimeters square have been ruled out. So we decided to ask ourselves a question that with all this information that we have got now, we can theoretically compute relic density. It has been measured very accurately, and very strong limits are put on its cross-section. That is this guy here. So can we use these 3 pieces of information and ask a question and answer, how light can a SUSY dark matter candidate be and still be a viable dark matter candidate? What is meant by that? That it should predict the value of the relic density, which is at least smaller than the observed one. Because if it is smaller than the observed one, you can say maybe there are multi-component dark matter. So at least it has to be smaller. If it is equal to it, all the better. Then the second is, but here this, as I remind you, this depends on what we assume for the thermal history of the universe. So use standard thermal history at this point. And it should be allowed by the direct and indirect detection of constraints. I mean, this is obvious. So with these three, what can the theory, what regions of the theory parameter space are allowed? So this is the question. At least if I've been able to set the question clearly to you, I'm happy. Because now I'm going to rush through the rest, which are technical, and which only my technical friends would understand. So the relic density calculation, now what is nice about supersymmetry is that in a given model, the relic density calculations and also the dark matter detection cross-sections depend on the same parameters, which means it's the same set of parameters which affect both your calculation of relic density and your calculation of cross-sections of direct and indirect detection. So this is what it is. And what we knew as thumb rules was that if the dark matter candidate is a purely Wien-like or purely Higgsino-like, it will have to have masses of the order of 1000 GeV. So that is not the candidate that I am looking for. I want to see if there is a possibility of having a light neutral, and to do that I have to play some technical games, but one can still get it. And in fact, this is where we began our story in 2000 when no Higgs boson was found, no evidence, no information was there about supersymmetric masses. And what we showed at that time, the density measurements, what I showed you as 0.120 plus minus 0.001, at that time, the measurement of relic density was 0.1 less than omega h square less than 0.3. So you see what was the wide range of allowed relic densities by those measurements. And what we had shown at that time is that when we get the Large Hadron Collider, we will be able to look for what are called invisible decays of the Higgs, and we should be able to check whether the dark matter candidate is allowed in this mass range where the Higgs can decay into two neutralinos. And we already had particle physicists already an idea of the Higgs boson mass that it would be around 120 GeV. So this particular plot uses a value of 120 GeV. 125 is the current value. So till the dark matter detection experiments came in full swing, the collider bounds and the measurements of the omega h calculations of relic density, that means basically the theorist ruled the game. And actually this condition continued till 2017 when, and as I said, in between, before when the collider, after the Higgs was found, we had actually shown how an invisibly decaying, how do you see an invisibly decaying object? So actually we had made some suggestions and which were followed by the experimentalists, and this is how you can actually look for an invisibly decaying Higgs. So now we come to this situation where we have, now we have this situation which is completely different from 2000. We have precise determination of relic density, we have very strong constraints from the direct detection, we have the LHC searches for electroweakinos saying that we have not seen anything. Then there is a Higgs detection and the measurements of the properties of the Higgs which get affected by the existence of supersymmetric particles. There are precision calculations of the Higgs mass which also get affected by the supersymmetric particle masses, and the measurements of the invisible width of the Higgs, which, as I said, we had suggested a method and which the experimentalists followed. So with all this information, what can we now say? From that funny plot which I showed you here, where everything was allowed, a lot, because green means allowed, okay? So a whole lot of things were allowed in 2001 by experiments. But now what happened? Now we did this in 2017, this exercise. And as I said, I'm going to analyze it in what is called the phenomenological minimal supersymmetric extension of the standard model. And then the number of 123 parameters are reduced. There are only a handful of parameters on which everything depends. And that's what I will show you the results on. You don't need to look at this. So what did we do? We make sure that a given point is allowed by the variety of the constraints coming from the Large Hadron Collider, from Large Electron Positron Collider, flavor constraints coming from the B physics, Higgs physics, calculate the invisible branching ratio for the Higgs. At this time, mind you, good measurements of invisible branching ratios were not available. This is 2017. And then we calculated the expected direct detection cross sections, calculated the relic density, and only if the ratio of the relic density calculated to the observed one was less than 1, we said we will use that point. And then what did we get in 2017? Very nice, in fact. What I plot here is allowed mass, the mass of the dark matter particle, and if the region is indicated by a green color, that means that was still allowed by all the experimental constraints at that time. And the blue meant that this was something that could be, and this also actually was allowed, but also could not be probed by any data available at that point. So this is something future experiments will do. This is what we had seen. And there were two deep valleys, one around half the Z mass and half the Higgs mass. And we were very pleased. We said, okay, this is allowed, and maybe the future experiments at the Large Hadron Collider, at the International Linear Collider, can look for the invisible decay of the Higgs and can look for the light dark matter. So we were quite thrilled. It was allowed by all the experimental constraints at that time. Came 2018, and I showed you the first plot from xenon 1 ton. And you see the number of points, this is the same plot, okay? Same points from here, and all the allowed points are gone. Near the Z pole, we had almost no points left, and near the Higgs, half the Higgs mass, we had a few points left. So we said, okay, now we need to do a little more careful study. And also we had left sign of one particular parameter called mu to be positive, so we decided now we will be a bit more careful, let's do this. And that is because other people had done some studies which had shown that they had found many more points in this region that we had found none, so we decided we will do a little more exploration around it. So we did that, and that is where the final result that I want to share you comes in the next two slides. So this we did in June 2022. And we had this paper ready, and what we found was that what you see here is that the direct detection cross-section, there's a new experiment called Panda X. I showed you from xenon 1 ton to Panda X, there was a factor 10 improvement in certain mass regions. So we found that after our serious studies, that green means always allowed. So what we found is that for the positive value of mu, we found no allowed regions for mass less than mz by 2, which is 945, and no points allowed, many points still allowed for m Higgs by 2. So we were quite again thrilled. And what is meant by the yellow points? Yellow means that they're allowed, they give the right relic. So first you do whether it gives the right relic, then you ask whether the LHC constraints allow it, and then you say, okay, now how can the LHC at high luminosity look for it? That was our whole purpose. And then of course, when we did for mu less than 0, which was the same thing, we did actually find a few green points at mz by 2 also. So we said, okay, now so we actually studied great detail, spent a lot of time and told our experimentalist friends, yes, you can look for these points, and then you can, if supersymmetry is there, you should find it there. Then came the experimental result in, this is July, this new result LZ, and now everything that we thought was allowed is now disallowed. But that is what I meant by saying that now data are really telling us that a low dark matter particle, which has a mass less than mh by 2, is highly, highly disfavored. And whatever is still very allowed, because there are a few points that are allowed. I told you always here now this thing has slightly changed. Here there is a different color code, but whatever are the points that are there, the deep colored points are still allowed. So you would say there are still few allowed points, but what we have seen at these allowed points are very close to the limit that LZ has put, which means that, and LZ has just given results for 60 days of running. So in the future, it's going to be able to probe them probe them very accurately. And these points here, which are way below LZ also, these points are going to be probed by the invisible Higgs bit measurements, which I cannot now, I do not want to go into. But what it's really telling us is that the majority of the, and if, particularly for mh by 2, the region at m chi1 not equal to mh by 2 is simply ruled out, and the other regions are also highly disfavored. And not only that, that is something that the very upcoming experiments in the Large Hadron Collider, as well as the direct detection experiments, are very soon going to be able to rule out for you. So as I say, it's a negative result, but what it's showing you is that the power of different measurement tools and the importance of different measurement tools to be able to probe a particular small region of the theory space. So it's a big game and a long game for particle physicists. I just wanted to share with you the kind of work that one has to put in even to rule out something. So that's really the conclusion, that the WIM paradigm for a light LSP in PMSSM as thermal dark matter, I have put all kinds of, as you can see, all kinds of qualifiers. It's only because I'm assuming standard cosmology. It's only because I'm assuming PMSSM. But let me tell you that even with these kinds of qualifiers, it was not possible to make this negative statement till very recently. So I wanted to share that with you. The case is different for non-minimal extensions, and in fact, we are working on that. What I did not discuss, which is even more exciting, that even if I didn't demand that the relic was less than the observed relic, and say that maybe I don't understand early universe, something strange happens in the early universe, and it still allows me to have a dark matter candidate in that parameter range. What we did show is that in that case, your Large Hadron Collider will be able to probe it and tell you it doesn't exist, which is kind of very exciting. That even if you were to remove the assumptions of that your knowledge about early universe, you still can probe with the Large Hadron Collider the entire story, which is very exciting, at least as far as a particle physicist I feel. And as I said, therefore, all the scenarios can indeed be tested at the high luminosity LHC, at the International Linear Collider, and the future direct detection experiments. So this is just to tell you that the particle physicists usually have to trudge a long, long way before they can draw a conclusion. Thank you very much.
Thank you very much for that nice talk. And we have a small memento that we'd like to present to you.
Oh, yes.
I'll just get the slide to get the next. So our next talk is by Dr. Ramaswamy. As you again heard in the introduction earlier this morning, he was the former secretary to the Department of Science and Technology, Government of India. And even before that, he was in our neighborhood at the Central Leather Research Institute, where he was the director. And today he's going to talk about the changing landscape of Indian science.
Thank you, Chair, and thank all of you. I thank Dr. Ravindran for giving me an opportunity to be here today and join the celebration of the 60th year of IMSc. Of course, both Balu and Rohini shared their excitement of doing their own work. And I'm such a state that I cheer the work of other people. And it so happened when I was a scientist in the Leather Institute, whenever I get into states of depression, which most of us do, my hiding ground used to be math science. So people like Balu, Bhaskar, Simon, they were all companions. And I was very happy to see the video today, where many of you shared the happiness of work done here. I think so this is a new year, and I thank the IMSc for giving an opportunity starting this year with this happy frame of mind. I think there are very few people who enjoy their work, and there are some here in this institution who have made their home of professional life and enjoy, and that's very nice to be here today and starting the 2023 on this occasion. And of course, when you are a scientist, you do your own work. When you are like me, you enjoy the work of other people, you celebrate them. And it's very nice that the video that you presented, that how math science has contributed to the landscape of the Indian science. And let me share with you today the changing landscape of science in India. I did not call it Indian science, science in India. And there's a specific difference in this Indian science versus science in India. And let me dedicate this to the tireless efforts of the founders of math science on its 60th birth anniversary. And to me, IMSc has remained a case of small is beautiful in the Indian science landscape. There's here 48 people, and that's not a big number. And that's the beauty of this organization. And I have managed very large systems. That's what you appreciate. When you're a part of a change, you don't observe the change. You have to outside the change to see the changes that take place. So I'm going to talk to you about the changes that take place being an outside the science community as somebody who observes it from this process. As one would really, I mean, I'm not a kind of guy who goes back to the Vigyan and Aryabhatta levels of systems, because they're all fantastic. But I think it's preferable to start with something that we could observe and observe process. And if you look at this post-1900 time, 1920s used to be a fantastic period of Indian science. Truly, science in India, some of the very best contributions to this country happened during this period of time, during 1900 and 1947, before our independence, when the government had no contribution whatsoever to support Indian science. There was no enthusiastic. These are individuals who made a fantastic status, and we, however, enjoyed a highly developed status among the developing countries during that period of time. And there's many lead scientific contributions matching the very best of the world emerged from these Indian scientists. And of course, when the 1958 Scientific Policy Resolution was promulgated in this country, it was ahead of NSF in the United States. And it was a developing country, developed a very emerging country, developed Scientific Policy Resolution in 1958, of course, drafted 1 3/4 page by Homi Bhabha and Pandit Nehru, read out in the parliament. And that tells you, conveys a principle, articulation of a principle that India's independent nation will support Indian science. That's the expression of political will. On account of several limited investments and changes in the external environment, I would say between 1981 to 2001 was another period of, Rohini talked about dark matter, just a dark period in this process of time. Because we could not make the kinds of investments that are necessary during this period of time. While I would not languish on what did not happen, I'm going to present the new year with the positive statements, what have happened since 2003, which are in the positive directions. And I would say, since 2003, the 2003 is a Science and Technology Innovation Policy promulgated by Vajpayee government. India started to regain some lost ground in volume space. And sometimes we have to be careful that we do not overlook what has not happened when things could do happen. So we still remain a fringe player in the global landscape. We have begun well, the best is yet to come. So I will make that statement before I move on to the next place. And if you look at this changing national space in terms of S&T space, prior to 1947, you would see Survey of India, IMD, ICMR, all that happened. Primarily because, for example, Survey of India used to call themselves organization the GOI, Government of India. I think we need to look at people of India, no, not government of India. Research institutions were really developed. Survey of India, which is, in fact, you realize the survey, the Guindy Engineering College used to be the survey map system. They chose the best location for themselves. This is 250 years ago. So Survey of India really created the a database for the British rulers to get what they can get from here. And that's the basic process that you have. But very few universities, extremely few universities at that point of time. 1947 to 71, remember the 1947 when India became independent, the life expectancy of an average child of Indian was under 25. Therefore, there was a real starvation in this process. At that time, we had BARC, DRDO, UGC, IC. IITs were generated during this period of time, and math science belonged to the same legacy. It turns out that Alladi Ramakrishnan centenary is 2023. He's a very clever guy who got his institute done at his 40th year or something. So there will be a centenary of 60th year of IMSc and centenary of Ramakrishnan. Alladi is the same year. And all that happened during this period of time. And we must remember, in the formation of IMSc, there's a role played by C. Subramaniam. Well, I would say that Pandit Nehru had a romance with science. I think Subramaniam married science. Therefore, he was a very important creator in formation of math science itself. And during this 1987 to 96, and after this Green Revolution, the government of India realized that there need to be a science ministry. So they decided to locate the Ministry of Science and Technology with the PL 480 go down. So even today, DSC remains in this PL 480 go down, and to convey that the science has a contributed to society's process. So the Green Revolution was in some sense a change in the directions of the science investments and political processes. Primarily, if we look at this today, we're not going to the details of those. Today, we have 42,000 colleges, 993 universities. We have 9 science departments, not 580, 680 national institutions. And when I went to the Department of Science and Technology, the number of full-time equivalent scientists of this country per million population was 131. And it was probably slightly higher than the number of country to which we don't want to lose a cricket match. So this was a very small number. And the number of people publishing papers in Web of Science was in thousands. Today, we are looking at 330,000 full-time equivalent systems. Therefore, that's an expansion that is happening today in terms of scientific activity in this country, in terms of volume space. And say, in terms of intergenerational transitions in science, pre-47 is truly benefits to the rulers in terms of data and those kind of stuff. So establishing S&T infrastructure, this IIT, CSR labs, and scientific policy resolution. And then there is this funding agencies came in this crisis, Ministry of Science and Technology, Department of Science and Technology, and DPT, and so on. And they truly, 1985 to 2002, where we had limitations, but it is the refurbishing and modernization of the infrastructure that happened during this period of time. And in 2003 to 2022, we have talked about aspirational changes in the growth of Indian science in terms of processes that happen, and all that big thing that Roni talked about in terms of participation in CERN experiments and LHC and so on. All that happened during this transitional phase of 2000 plus. So scaling up R&D investments, and today we are talking about aspiration to be top 3 in the world, and you're looking at aspirations of current generations. And I divide Indian generations into 5 types. A generation ahead of mine, the generation of freedom struggle. They really work for Indian freedom and kind of loyalty and sacrifice and so on. I consider myself as a generation of deprivation syndrome. when everything, nothing was available. So even the only available thing was air, even water was not. Then there was this question of a comparison syndrome. Compare America, England, now China. There is the globalization of trust. I consider the present people who are doing science in this country are aspirational generation. Generational aspiration process, and they are open to new challenges to organization. But then the institutions established, like mine in the Leather Research Institute in 1948, April 48, they have a legacy. Overcoming legacy is non-trivial. You must remember in the Dravidian kingdom, in whether Karigala Sodan allowed the movement to this place or not will happen. And these are realities, and one has to recognize these are challenges that we have to deal with. But whenever we talk about a nation, we must remember the changes should not be seen in shorter time space. You need to have a longer time space for changes to happen in a mural. It turns out, looking at the National Education Policy in 1966 was essentially a radical restructuring away from what was prevailed in the British model. Then there was a need for social integration in the National Education Policy of 1996. India is a country of immigrants, over 2,000 years of history. That's all kinds of divides. And how do you, our energy spent on integrating itself is quite significant. Forget about the growth. Stability is more important than growth in this country. Then there's a question of standard harmonization, 1992. On 2020, you're learning optimization. Because it has to go through a process wherein the basic needs are bridging the divides and then raising the standards. And these are the policy statements that happen. And you're looking at it in terms of I'm sorry, this particular thing has not happened, where there was a science policy based system not stored on this. Doesn't matter. It turned out that when I was called upon to be the Secretary, Department of Science and Technology, I gave myself 10 targets. What will I do if I went to the Department of Science? And what are the major changes that are necessary in this country? And first was democratization of Indian science, from a patronage to rights, citizens' rights. And they therefore bring performance-related in those processes. Therefore, one doesn't have to go through the peer review process the way that we operate. If it is you performed, you need to claim it as a matter of right. Then the debureaucratization of R&D systems, funding, it was an act of parliament, because in a democratic country, the government of India rules will apply as long as everything else, the financial provisions will apply everywhere. But if you want to create like export promotion zone, you must create a small system. The science funding requires autonomy. It does not require some 12 signatures for every 5,000 rupee sanction. It turns out that the DST releases something like 18,000 sanctions, and every sanction requires 12 signatures. And therefore, this question of the said Act of Parliament have set different sets of rules. And there is this question of rejuvenation of research in the university system. At the time when I was a student, I grew up in AC College campus when GNR was at its very best. It turns out 12 Bhatnagar Prize winners of the 70 from Tamil Nadu came from AC Tech. It was a great system. Now, that university system used to have a big share of contributions to science. When I went to Delhi, 15% of contributions came from the university system. How do we rejuvenate the university system? The national labs are great, but universities have the students. Therefore, the nucleus has to be, the spring of research has to be university system. Then this question of talent attraction. How do you bring talent to come to basic science? Pave a career path, give an attraction in this process, and address the talent supply chain. Then there's a question of globalization of R&D, where it brought reciprocity, parity principle. Dr. Chimbaram talked about how the fatigue, somebody talked about fatigue of the donors. We said, we don't want your money, we will invest equal, but we'll share commitments equally. There is this question of popularization of science, gender parity in science, social contract of S&T, technology not as a product but as solutions, convergent solutions, and then the science to startups. These are all the 10 agendas were taken. They were converted to 74 new schemes during my time as Secretary, Department of Science and Technology. All are implemented. Inspire is one of them. Now, after 2015, okay, these are 515, what is the IST Science and Technology Innovation Policy of 2013, talked about democratization principle. The way we developed it, we wrote the script, and then I had 7 institutions organized meetings in different places. So 5,000 people participated, and then we drafted this, and I had Ramachandran write it in a language which people can understand, put it on the web, and they had available for people for 21 days, and then it was followed up. And the formation of a server funding and promotion of research purse, Inspire, and several schemes that happened, I talked to you before. Now, that has been continued also in 15 to 21. The same principles are retained. The process adopted for formulation of a CAP 2020 is bottom-up, not a top-down model. And you're talking about establishing a foundation with process simplification. That's a National Research Foundation is a concept with process simplification. And you're looking at establishment of RUSA on mission mode for the university system. Several schemes focus on individual fellowship opportunities. And this question of popularization of science, the Indian Science Festival and the India Science Channel, gender parity in science, women empowerment in various schemes, including this Kiran, and this question of social contract, the linking STIP as a social contract metaphor is built into our processes, and technology mission mode programs, and of course, today, Atal Innovation Centers is a part of this process. Therefore, what it conveys to you, it's not just one government, intergovernmentally, how things sustained in science in this over a period of time. And this question is, what have we done initiatives and what kind of evidence that something is happening? So basically, I will talk about 8 processes: increase gross enrollment ratios in higher education, and increase in full-time equivalent scientists in the R&D sector, and number of authors in ISI scale publications. University research R&D innovation, rejuvenation of university research, number of publications in peer-valued journals, number of essential science index, the highly cited papers from this country, and through a globalization of R&D in terms of databases, and improving competitiveness, patenting activities, and startup ecosystems. And I will present to you data, because I am one of those guys who believes in evidence-based in decision making, because I don't believe in subjectivity. That's what I have learned in life. Therefore, I will present to you the trends that happened here. This is the enrollment ratio of students in higher education in this country. And don't look at the numbers, but look at the trends. It turned out when I was trying to set up this Inspire scheme, I asked for data on the number of children who passed school final in this country in 2005 in class 10, 2007 in class 12. It turned out 35 lakhs. And it so happened, I asked them, how many of these children were top 1% in the class 10 in 2005 and class 12 in 2007, 20,500. Then I asked the question, how many of them were small towns? 62%. How many of them are girls? 52%. I came back and said, Inspire will not have competitive examination. We will take this indications processes. And it turns out, at that time, 8% went to college. 8% went to college of 35 lakhs. Today, 1.7 crore is the number of children who pass the school final, and 26% is the people who go to college. And that's the number of students who go. This is the gross enrollment ratio in terms of percentages, from 8 to 25%. And it turns out that NEP 2020 says that India will have 20, 35, 20, 50%, Tamil Nadu 52% already. Now, in terms of increase in FTEs, in number of publications about the super millennium, you're looking at number of FTEs in terms of R&D growth, in terms of the per million numbers, and this is the number of authors, number of papers, and number of authors growth process. There have been a 6-fold increase in the number of people publishing papers in Web of Science, science citation based in the journals in the last 20 years. And that's the number game that expansion took place. It turned out that when I used to be in the government, people used to accuse me of diluting the quality, but I said this, India needs the volume base for which any excitements can happen. Then there is this rejuvenation of research universities. These are the Web of Science papers in the top 28 universities in this country, you can see the change that happened, slope change. More number is unimportant. The direction of change is more important. And you're looking at this in terms of the citation, the H indices of the universities. It turns out when I had this PERS scheme, it was again a democratization process. We came back and said in 2008, I asked some to find out 50% of publications came from how many institutions in this country? 35. How many of them are universities? 14. I said, these 14 universities, in spite of all the limitations they had, been part of the top 50%. Then we said, if anybody had, how many research IITs had H index above 50? 1. If three universities had H index about 50, we came back and invited them a grant, gave a research incentive grant of PERS of 30 crores for 3 years. And they can spend the way they want other than anything in a building. I gave them the autonomy. Then it is 40 to 49, they got 15 crores. 30 to 39, they got 9 crores. 25 to 29, they got 6 crores. And that same system is a 10-year aggregated data, 1996 to 2006. Then we came back and shifted by 2 years. 98, 2008, the 14 had become 44. And it turns out today there are 3 universities H index above 200, about 200, okay? And there are 23 universities between 100 to 199, and 35 above 50, and every one of those 44 universities funded under PERS had gone into the 100 mode. So that is a rejuvenation process. Now, in terms of rise in scientific public in the millennium, you're looking at in terms of 2 databases, the Web of Science and Scopus databases. You can look at the manners in which the slopes grow. It is a hockey stick change. So changing dynamics tell you there's something positive happen, and there is no disruption in terms of slopes and changes and so on. Governments come, governments go, but there's eventually science do the scientists. Government doesn't do science, equipment doesn't do science, scientists do the science. So all that was necessary in this country to provide a little enabling role in terms of resource and support, and that is what is happening. And today, when I went to Delhi, we were 15th rank in position. And it turns out, in terms of Scopus database, we are 3 today. 3rd in Scopus database. And in terms of Web of Science, we are 6, but that 3, 4, 5, 6 are all clubbed. So it's a very small change. And it turns out the number of highly cited papers from India in 2004 was 0. And we looked at the manners in which we said, if you want to play the game of citation, you must speak the language of the Western world. Because they are the guys who do all the dominated Western. But science is today, whatever you may say, it's dominated by Europe and the US in terms of number game. So we said globalization process happened, and in terms of we made interactions possible, and it turns out that this is the lower curve. This is India. Do you realize that in 2021, India is 3rd largest in terms of highly cited papers after China and United States? All these nice collaborations, that CERN collaborations, all that bring you citations. And that's a process of globalization. India cannot, that's why it did not use the word Indian science. Talk about science in India. And these are relative comparisons in publication activity. There's a comparisons being done. You can see in Scopus how we have moved up. I have left out the United States and China because the scales are very different. So I have come, you can see India has moved up in the scale from here to here. And you look at this is Web of Science, all those countries, which are France, Canada, Italy, Japan. So many of them, we are in the group listed, and it so happens that we will become 3rd. It's a question of time because the growth rates are very high. And in terms of patenting activities, these are the kind of changes that happened. in terms of patent for work done in this country, but the patent of people for value work done filing in this country, all that process happens. So the 2004 share of Indians filing patents in India has registered continuous increase. And that's a 2014 based system. And that's a startup ecosystem, which is really a really important part of the development process, because the science is great, publications is great, but you have to convert that also into some sense of economic activity for the nation as a whole. And that's a startup process. And it turns out today we have become the third largest startup ecosystem in the world, with a year-to-year growth of 15%. And we have, in fact, as of 2022, we might have moved to the second, moved up there as well. And the total value of the equities, and it turns out the number of women entrepreneurs stood at 14 and a couple of years ago, and it turns out that Bangalore is listed in the top 20 leading startup cities in the world level. Now, how do we do that in terms of science? I come to mathematics, math science, and don't talk about mathematics, Balu will be very unhappy with me. And I had to be living with Balu all his life, so I have to be careful. So it turns out that I take this 2017-21 and 97-2001, 20-year difference. Because to me, that's a time window with which changes can be observed. You can't see it year to year. You have to look at time window, and I also don't talk about a year, I take a duration, 5-year duration. And when you're looking at it in terms of the chemistry, 97 to 2001 to 2017-21, this is the Web of Science database, there's a 241% increase. And physics, 184%, biology, 175. Suddenly, because I'm math scientist and bold, it's 287%. And that's a fairly big change. Of course, I will say, Balu, look, you followed the publishing less during 97-2001. Your base was low. And engineering has really remarkably changed, and so has material science. In computer science, it turned out in 2003, the total number of people who finished PhD in this country, as India, was 33. Whole country is 33. Today, we have become third largest in terms of computer science of outputs in terms of publication base of the world. Now, in looking at it in terms of rank movement, I talk about the chemistry, we were 10th during the 97-2001, today we are third. This is Web of Science. This is 11th to 4th, and biology 20th to 9th, mathematics for 13th to 5th, engineering 12th to 3rd, and material science to 3rd. Fundamentally, without getting into the details, we moved from a double-digit rank to a single digit across the various spectra of various disciplines in the process. Of course, these are data from Wikipedia, so I have no authenticity for this process. I will disown the responsibility for the data. This is Wikipedia, they backed up yesterday, and therefore you are very welcome to go and check this Wikipedia data. And I have reservations about something myself, but that I will not share. This is the purchase power parity investment of different countries as claimed by Wikipedia, okay? And it turns out that India has been grouped as the 4th largest investor. And 3 years ago, we were the 6th largest investor, okay? Therefore, we are somewhere between 6th and 4th. And this data tells you the kind of gross expenditure on research and development on purchase power parity terms. And what I have done here is to plot the gross enrollment investment of various countries as a percentage of the GDP against the number of full-time equivalent scientists per million population. These are not my creation. This is the way R&D intensity of nations are done, compared worldwide. And that's the process in which it is done. R&D intensity is measured in terms of full-time equivalent scientists per million population, and then percentage of the total expenditure of R&D as a percent of the GDP. The golden benchmark is 2% of the gross GDP and 4,000 scientists per million population. That's a number. And when I was in the government, I used to write and gave it to Prime Minister, we'll invest 2%, knowing fully well we cannot. Okay? I tell you why. If you want to invest 2% and above, the number of full-time scientists, full-time equivalent scientists, had to be more than 1,200 minimum per million population. Otherwise, you will invest, and as Dr. Chidambaram used to say, they'll suffer from indigestion problem. You'll invest, but they'll know how to digest. You need people to do this process. And it turns out that India's investment was here moved up this particular point. So this is Asia, the Korea, China, India. And for the first time, you recognize that Asia is moving into the science space away from Europe. Because it turns out these are the countries which I will call them as low resource setting countries. This is full-time equivalent scientist rich, FTE intensive countries. This is resource GRD investment countries. These are highly resource intense countries. It turns out these countries which are in this domain invest heavily, and the research results come out of that huge investments have to be paid for. You need to get a return from this process. It turns out these countries which are investing significantly, including the United States, do not have the capacity to serve the R&D needs, innovation needs of the countries in this quarter, because they're too expensive, unaffordable in the process. It turns out India is the only LMIC. There are 55 low-income group countries, 55 low-middle-income group countries. There are 90 countries. India's investment today is 93% of the 90 countries. And if the 90 countries required R&D, we are the best position to be able to provide that solution. And it turns out that Indian investments are 94% of the total investments of 35 low income and 55 low income countries. And our investments here have a certain value to the world at large. It turns out the total investment into R&D as of the post-COVID scenario is $2.1 trillion. And if you invested at the same level as here, or the United States, the total investments of the world to serve the population of 7.5 billion will be $9.9 trillion, not 2.1. So the 2.1 at the level of investment of the United States can serve only 35% of the population, global population. Therefore, if we really require the 66% of the global population being bypassed with that high resource intensity model. Therefore, we have an opportunity to change things around. And I would say, change the Indian science sector, the new millennium profile, and credible arguments were advanced that early initiatives have found the foundation principles. At the turn of the millennium, successive governments have focused on building a viable superstructure for Indian higher education and R&D system. And evidence for accelerated development has been presented. All are verifiable data, public domain data. I have not cooked up anything. These are from Scopus database or Web of Science database. All are known. You can go back and check them up. And although the position of India in the global R&D has improved in volume space, she still remains a fringe player. And therefore, more is needed from Indian researchers for the nation gaining her rightful place. And I believe math science could show the way. And it turns out that Tagore, very interesting man, it talks about the tendency of modern civilization is to make the world uniform. Let the mind be universal, let the individual should not be destroyed. And I believe in the gross amplifications of the macroscopic space, let institutions like IMSc retain your individuality. Don't get burdened by the averages of the lot. So all modern civilizations have the cradles of brick and mortar. In India, it was the forest that our civilization had its birth. and it took a distinctive character from this origin and environment. This is from Tagore. Okay? And education, it so happens that the ancient Indian civilization talked about education, purpose of education is to reveal an internal perfection, self-realization. That's what the purpose of education is all about. Theory of anomy would say that man is born lawless. That's the Western world. Man, education makes him law-abiding. It turns out Britishers made us law-abiding. Let us look at Indian science in India, which is liberated from the natural processes. IMSc has tried to retain its individual in research and higher education. I think small is beautiful. Nimble structure provides the mobility and autonomy. Long live the IMSc. Thank you very much.
Thank you very much for sharing your perspectives and also for this very positive note. I'd like to present you a small memento as a token of thanks. So we now come to the last talk of this session, and this talk will be given by Professor Sudeshna Sinha, who many of us here know her very well because she was a colleague here for several years. Currently, she's the Deputy Director at ISER Mohali, and some of you may recall that just last month also she was here and gave a very nice public talk, which we heard. Today, she's going to tell us something more about complex systems.
Sorry to stand between you and lunch for which sling bag? No, I think I'll sort of negotiate this. I'm kind of, I should put this on her, no? Where's the, oops. Yeah, there. Okay, well, first off, thank you for inviting me to the party. I'm absolutely delighted to be here. And though Kapil and I are, have been very nomadic over the years, math science still is the place where we have had our longest stretch. So it holds a very special place for us. On a personal note, I think I should also just say that it gave me the space and the openness to do whatever research I felt like doing, the support to do whatever research I felt like doing, and so I'm truly grateful. Okay, so as Meena just said, I was here a month ago, and I had to sort of scramble around trying to find out non-overlapping science to talk about today, and I thought I'll pick up this thread on complex systems because I know there's a lot of expertise in the audience from math science on the subject. So one of the things about complex systems is that the good news for us is that the Nobel Prize of a couple of years ago legitimized this word. It's no longer one of those, slightly shady words where, which you use to push things under the carpet, like a cover-up of stuff which you inadequately understand or, you don't have technical words for. Somehow it was very nice for us to see the word complex systems right there in a citation for a Nobel Prize. Gave us some legitimacy. And the other thing which I found very interesting about the Nobel Prize, because a lot of physicists were a little upset that they did not recognize the names of 2 of the 3 people who got it that year. And that was interesting because it actually tells you how truly interdisciplinary this part of physics is. That 2 of the people who, engaged in complex systems research were actually climate scientists. So, we would like to take this broad picture to, give us a sense of where the field is headed. I'll attempt a very, actually, I should have not written precise, I should have probably written imprecise description of complex systems. No precise definition, I believe, exists, so I'm safe there. Let me just put 3 things which I think should be in a complex systems research agenda. One is it should involve a large number of interactive components. Obviously, if the components did not interact, they would just be, essentially reduced to single components, and no fun in that. And if, of course, even when you put them together, it is just a sum of parts, then it does not qualify to be complex, okay? That also doesn't cut it. So somehow it must do something, and we use the word emergent behavior, maybe use or abuse it occasionally, to say that it shows some new behavior that is somehow more than the sum of parts, and that we are happy to call complex. And in some sense, I should also basically, alert people that at some reductionist sort of picture, you might think that everything that's happening at some level is determined by the physics which operates beneath it. So you have some foundational physics which everyone likes to do, and then stuff builds up sort of automatically on top. But the thing is that the hierarchy is actually very, very complicated. So science at X is not just applied science Y. That is not how it works. And once we recognize that, it also legitimizes the more complex science which follows it. So each stage actually requires new laws. So when I say laws, probably I should have put it in quotes, but at least new concepts to make sense of it. So I had this thing which I stole off the internet, let me be honest out there, but I really like this little cartoon of what mathematical modeling is all about. Now the thing is, a lot of us in complex systems research do what is called mathematical modeling. It's one of those key things which helps us make some sense of phenomena which qualifies as complex. So what do we do? So we are trying to make a simplified mathematical representation, and the thing which we need to put in there is the key feature. What we think is the key feature is where your imagination comes in. But the key features which play the essential role in interpreting the observed phenomena. So that's what you want to do. So the best models should be able to do it, just like Picasso has got the essence of that, very specific looking, somewhat nasty looking bull with a stylized set of lines. And so there's of course a whole zoo of models. I mean, people do what they feel like doing, as I said in the beginning. So you could have these very simple cartoon-like, what we'll even actually call toy models. And of course, people go to the other extent of having very complicated and detailed things. And obviously, there is space for both. Both are useful. Researchers do both things. But there is a trade-off. So the trade-off is that, in one end, you will get some broad understanding, So if you make a toy model, it would sort of indicate broadly how things work. And on the other hand, if you wanted quantitative predictions, you would like to make your models which are closer or at least analogous to the real thing. So more like a copy of the real thing. Okay, so it's this end versus that end. And so what I thought I'd do here is that I'd maybe indicate a couple of specific results which I got actually sitting right here in math science. So I thought, it's a good place to share it with you all. But before I do that, I wanted to give you a small, quick recipe. It's one of those, very, very basic ingredients of complex system models. So the two ingredients that you really must have is a local component. So there's local dynamics. So people like us who do dynamical systems are in business because we know very, very nice, interesting, complicated, chaotic, low-dimensional things, and we can just stick them there. And the other thing, which came more maybe from the statistical mechanics side, was the importance of connections. So you have the local component and you have the connections. You put them together every which way you want, and you study them and, and see what you get out of it. So the second one deals with links, you can think of it as a graph of the underlying connections and the coupling forms. And here is a little table of what I call a hierarchy of models. And the way I have put it is to say which class of models considers various important things, that is space, time, and the state variables, either as continuous, that is represented by a real number, or discrete, as represented by integers. So class of models, for instance, at the apex in some sense would be a PDE, a partial differential equation. Space is continuous, time is continuous, state variables. Do note that the state variables would be the closest to a experimentally observed quantity, like maybe temperature, pressure, velocity, chemical concentration, population density, as a lot of people do here, charge density, etc., etc. So, so PDEs are there. Then a lot of people do what are called oscillator chains, where space is discrete, that is to say each oscillator is an entity, so it has a number, integer associated with it. But time is continuous, state variable is continuous, so you can write an ordinary differential equation for it, but at, distributed in space. The other thing which I love doing is called a coupled map lattice. So there is, space is discrete, as in there are entities on sitting, say, you can think of it on the nodes of a graph or on vertices, and state variable is continuous, but time is discrete. So it's a map. So it is stroboscopic evolution of the state of the system in time. And cellular automators, I would put a thing where everything is discrete, which of course computer science loves, and I will probably also indicate one or two results which use that class of models. But do remember, each class brings with it its own counterintuitive, flavor. For instance, very simply, if you had I don't know, a non-invertible, non-linear map like a logistic map, it's capable of showing chaos. You take a one-dimensional map with the same non-linearity, it can only give a fixed point or can run off to infinity. So, you can see how just discretizing it, so it is not just discretizing, okay? So you must remember each class of models brings with it its own validity, sometimes even being a more natural framework to understand something. So they are not just poor man's PDEs, is all I'm saying for the PDE people in the audience. Okay, so now a few specific things, and I'll finish whenever my time is up. So consider specifically a one-dimensional ring of coupled nonlinear maps. So when I say sites, you might think nodes, you might think vertices, if you think graph-like. So there are these integers, 1 to n. N is the size of your network, lattice, what have you. And each one of them has this real number, the state variable associated with it. That's your physical variable of interest. Now consider a very simple map, which is coupled to nearest neighbors. So it just talks, so I is a site talks to I plus 1 and I minus 1 with some strength of coupling, epsilon. And let us take the local map to be fully chaotic, okay, as complicated as it gets. So you string them together, and no surprises, you get, this is what we call a bifurcation diagram. So running along on the x-axis is the coupling strength. And as you vary coupling, nothing, stuff happens, but it's all still a mess. And nobody is surprised. You had a fully chaotic map, you put them together, you got more of the same. Now, you consider the same system by taking the coupling connections and rewiring them randomly. So this was on a ring, okay? And now you take them and you just cut the links and paste them to non-local positions. So connect a fraction p of randomly chosen sites to two other neighbors. So p equal to 0 is your nearest neighbor interaction, the ring, and p equal to 1 is a completely random graph. So here is a graphic. So this is from Watson-Strogatz. In some sense an obvious result, but made a citation classic partly because they had this parameter which modelers like. There's one parameter which you can sweep going from regular through the small, what is called the small world limit, where dilute number of random links are there, to the fully random case. So now we do this. Let me do the first one. I take that same old bunch of fully chaotic maps in a network where, of course, the network also changes, but at every point of time, it is random. So it picks up random neighbors as it goes along. And even if you forget everything else that I've said or feel too spaced out to concentrate, I just want you to maybe take this one, back with you. So here is the same bifurcation diagram. This is the coupling strength. But now look what happened. So these are still individually, intrinsically, strongly chaotic logistic maps at this parameter r equal to 4. So it's absolutely chaotic, no doubt about it. But when you put them together, now not in a regular network, but in a random network, this randomness of the connections and the chaos of the local thing have somehow given you something which you wouldn't have guessed. So this is one of the things which we expect in a complex system, that you get a surprise which you would not have guessed because it's so counterintuitive. So you have made things more random, and what you get is the stabilization of the fixed point. So this thing here just says that all the way from around 0.6 or so to 1, it's a large range of coupling. Every single map, so this I think had 500 logistic maps, all of them sit happily, stably at the fixed point, which is actually a strongly unstable fixed point for the individual map. Okay? So basically the dynamic random links has created this window of coupling parameter space where, put it a little more technically, the spatiotemporal fixed point has gained stability. Okay? And there is a certain bifurcation parameter, which of course we in the business like to put a number to. And as I said, so all the sites then are stabilized at the strongly unstable point of the local map. This is the takeaway from this bit. Of course, we are in the business of doing theory, so you have to do some stability analysis. As it happened, it's actually a little bit technically difficult to do, partly because the connection matrix is changing and is random. So, you know, the Jacobian is a little bit of a issue to do exactly. However, you can always turn around something which is a bit of an issue and see what you can make of it. Here, what I thought was that, okay, since the connections are changing, each site is seeing like a blur of its neighbors. So it's like a time averaged mean fieldish thing. And that, of course, simplified things. So sometimes when things are moving too fast, you see, you know, it's like, you know, you actually see something which is a near constant. And if we do that, one can do the analysis quite easily. And the end point is that you get almost no stable range if you have regular connections, whereas for a fully random connection, you get the largest range. So that is where the surprise is. So you throw in randomness in the connections. Of course, locally it was very chaotic anyway, but that connection, the randomness somehow killed the chaos of the local map. And this is a small summary picture of the analytic result, which is the solid line, a little bit of the kind of approximation for small p, and simulations from whole bunch of lattices. So when we get things like this, we are happy because, you know, that solid line is pretty much sticking to simulations. Okay. And this is just to say that, okay, I showed it to you for the logistic map. Anyone, including the referees, will say, but so what if I had tent map, would your answer change? Or if you have a circle map, would your answer change? And well, you don't expect it to change because what really is necessary is the local maps kind of instability parameter. And once that is there and it's equivalent, you actually get absolutely equivalent results. So that sort of is what we you know, say shows some sort of generality of the broad observation. So this was dynamic rewiring. So I took this map, and at every point I was switching around the connections. So not only was it picking up random neighbors, it was also doing it as it was going in time. Okay? What if we had random connections, but it was static? So, you know, I had a network, random in space, but not in time. So if I took a snapshot, it would look the same, but, you know, the next snapshot changes for dynamic, but not here. So what happens there is that actually what you got for dynamic random connection disappears in the limit of large lattices. So you're back to what you got for essentially regular lattices. And so now you have to make sense of this scenario, that not only is the dynamics on the nodes important, the dynamics of the network is also important. Okay? So that is maybe, this is a kind of halfway or whatever, two-third way summary. So the, two-third, okay. So I'll just talk very fast and finish everything. So yeah, so this is kind of, you can take back this maybe, is that the regular lattice gave spatiotemporal chaos, static frozen links gave spatiotemporal chaos, dynamic rewiring, that is switched random links, gave you spatiotemporal fixed point. These are not subtly different things. One is at one end of the spectrum and one is at absolutely the other end of the spectrum. So it is very dramatic, very, very stably different results. So that's the fun part of it. Okay. So of course, static and dynamic gave different stuff. So what do? You employ a whole bunch of students to do this, that, and the other, and check it out for different scenarios. And I'll just have one picture. Here actually the young person involved was a CMI student doing one of those KVPY things. So that's why I thought I'll put it. Has a little Chennai connection. So on one side is the time period of rewiring is 100, and the other one is 1. So this one is rewiring very fast. The other one is rewiring slowly. So when it's rewiring slowly, it opens up a smaller stable regime. When it rewires fast, it opens up a larger thing. So of course, we went across the spectrum, looked at different fractions of random links and different network rewiring frequencies. And this is what a lot of us in this business call a collapse of data. That is to say, you have to find out on the x-axis the combination of variables such that what you get on the other side collapses to a neat function, which would then indicate that that was the important parameter. So here, P in itself did not give collapse, F in itself did not give collapse, but the product of P and F, everything collapsed, which means that the real thing that was important here was a trade-off between how fast you rewired and how randomly you rewired. So you could actually get the same effect for slow rewiring if you had a lot of spatial randomness, or if you rewired fast, even 1 or 2 random links would cut it. Okay, this is in layman's language what this graph means. The next bit are just a set of pictures. Okay, so as I said, I had put a set of models. This one was coupled map lattices. The next two are, this one is going to be what would be called, oscillator chain. Okay, so this is ODEs on a ring and later on a network. Okay, and this particular one was modeling biochemical pathway of a 3-step reaction sequence. And for no reason, I'm just flashing that these were the equations. Okay. Now this is the result. So on one side is P equal to 0 means a regular ring. Time runs up like that, and the rings which are, and the cells which are 100 of them, 0 to 100 runs along the x-axis. Now when it's a regular ring, there is some sort of, well, disorder, at least to the eye, and if you get order parameter, indeed it's there, disordered. Whereas even if we put a dilute amount, this is P 0.05 disorder, very, very small amount of randomness, it sort of irons out this whole thing, which meant that all the cells essentially come to a synchronized state. So here, randomness aids synchronization. In the first part, randomness aided the fixed point behavior. Here, it is a cycle, but they become synchronized cycles. And indeed, this transition, this is just for the few people who are stat-mechy in the audience, that this transition is a P tending to 0 transition. That is to say, with the slightest disorder you throw in there, it very, very quickly goes to synchronization. I thought I'd show one more pretty picture. This was done by a student in ISA, and this was done well before COVID broke, 2013, so that's why I thought I'll show it. It's always nice to see infection spreading before the event. And this I also thought I'll show because it falls in the class of models which is a cellular automata. So these are SIRS dynamics on a network, but SIRS done as a cellular automata. Okay, so this fell in the third class of models. I thought I'll pick up one from each class. So this one was in the third class, whatever, cellular automata class. And this is one representative picture among many which he had. So there are these three panels. The time period of network rewiring is very fast on top, somewhat medium in the middle, and slow down here. Okay? So the slow down there meant that, so what did the top panel mean? As you see, there seems to be large peaks. So basically your infection spreading has given rise to these sort of, synchronized outbreaks, which is a dreaded word now. It wasn't in 2013. You could happily write a paper without feeling, anxiety. But this showed actually that if you have a random underlying network, you will actually give rise to synchronized outbreaks. Sort of, common sense in some ways too, but nice to see it come out of a model as well. And if you actually rewire very slowly, you have this sort of endemic, small, irregular background, but at least not everything building up periodically together. So here too, to come back to this whole thing of randomness gives rise to regularity theme, randomness gave rise to synchronization. So the central observation was this quasi-fixed low state, kind of like endemic, gave rise to the self-sustained oscillations, which you could think of as periodic outbreak if you switched links more frequently. Okay, so the disease cycles of these individuals on this network got synchronized, and stuff happened. Okay, so this is the last bit. 5 minutes. Okay. So the last bit is to show one more effect of a random link, and this time it is doing something completely different. So my student, well, the lead of this was Anshul Chaudhary, and so he was a really good student. So when he came and said that his program was blowing up and giving these dreaded NANs, of course, anyone else I would have said go and fix it and come back next week, but I had to take his thing very seriously. And so indeed what he had was, with a certain coupling scheme, his oscillators were giving unbounded growth under coupling. And this is a bit distressing for anyone who does dynamics. So what I went and told him to do, and he did very, very sincerely and well, was to take those same set of oscillators, which were blowing up, and when they were on a regular ring, I said, okay, now you change around the connections, put it on a random network, and see if the randomness in the connections reigns in your dynamics. And indeed, what happened was that the blow up, which was occurring for the ring, was prevented when you managed to rewire fast enough and randomly enough. Okay? So again, in some sense, the randomness killed the unbounded growth. So the infinities were reined in some sense. And this is the last figure from there. And this was a Fitz-Nagumo model, which is a sort of a model neuron, and he put it in a ring. And with his scheme of coupling, things were blowing up. So this red line here was his regular ring. So, if I let it go, it would hit the ceiling and beyond. So it's already doing, shooting up extremely fast. Whereas these guys here are the ones with rewiring. And this is the phase space plot. It's not showing as dramatically. So this red one comes in and then runs off, to infinity, and the membrane potential just blows up if it's on a ring. But you throw in a few random connections, and there you are managing to rein in everything into a nice bounded part of phase space. Okay, I had 2 more slides. I don't know whether to show it or not. Okay, I'll just show it since I think I have 2 minutes. So I just wanted to say that was random connections. But I had these two ingredients, local dynamics and connections. So I showed the part where the local dynamics was fixed and the connections were changing. You could do the same thing by keeping the connections fixed, but seeing how heterogeneity in the nodes affects it. And in more recent things, with more recent students, we sort of found, I've just listed it here, that heterogeneity suppresses chaos. So there again, more disorder, or at least more heterogeneity, more kind of variety in the constituents, did manage to rein in what was more complicated looking phenomena. And this could be asymmetry in the nodes in terms of the nodal dynamics, or it could even be time scales. So same sort of thing, but with ill-matched time scales. And this is actually an experiment which Puneet's group had done on this, and with oscillators. And this flat portion shows how things were, reined in, suppressed when things were heterogeneous, and this off position is when left to its own and just homogeneously doing something. So heterogeneity actually pulled it all back. So basically it's a way of seeing it is that, it has nothing else, there's no other solution which fits everybody except the fixed point. The whole point, of course, is the fixed point stable? That's the story, of course. Okay. And this is my last slide, and I'm done. So I just thought I'll give you a flavor, because a good part of what I said was done, in math science. So it falls under the broad umbrella of complex systems, more specifically linked local chaos maybe, and has some relevance to complex networks, where the basic point is that there is nodal dynamics and there's connectivity, and they play off against each other. And in this interplay is the surprise and sometimes counterintuitive things. And the counterintuitive thing which I indicated was that the random links can suppress local chaos and induce global spatiotemporal order. And also I sort of touched upon that these random connections can mitigate catastrophic blow-ups. I'm done. Okay.
Thank you. Thank you very much. Yeah. On behalf of IMSc, I'd like to present a small memento. We have to go to the yes. Okay, so that brings us to the end of this session, and we can all go for lunch. And as you all know, of course, we had a somewhat late start, so we are not on time. We will therefore start the next session a little bit later, but not very much later, because we do have a busy afternoon ahead. So instead of 2:30, we'll start at 2:45. So I think that gives everybody enough time to have lunch, but we will start exactly at 2:45. Please come back by then. Thank you.